In the vastness of space, something lurks. Silent, invisible, consuming light itself. Astronomers call them cosmic voids. Enormous regions of near-nothingness stretching across billions of light-years. These colossal empty spaces are not merely gaps between galaxies. They are fundamental structures of our universe, as important to cosmic architecture as the galaxies themselves. Yet we've only recently begun to understand their profound significance. The first void was discovered in 1981, a shocking revelation that upended our understanding of how matter distributes itself across the cosmos. Scientists expected to find a uniform spread of galaxies, like stars scattered evenly across the night sky. Instead, they found a universe more like Swiss cheese, clusters of matter surrounding vast bubbles of almost nothing. These voids are not truly empty. They contain sparse hydrogen gas, scattered radiation, and the mysterious dark energy that permeates all space. But compared to the cosmic neighborhoods where galaxies cluster together in filaments and superclusters, these regions are cosmic deserts, places where the density of matter drops to less than 20% of the cosmic average. What makes these voids truly fascinating isn't just their emptiness, but their behavior. They expand faster than the rest of the universe, stretching the cosmic web like invisible hands pulling at a delicate fabric. This accelerated expansion provides crucial clues about dark energy, the enigmatic force driving our universe's ever-quickening growth. Even more bizarrely, these voids appear to move. Recent observations reveal that galaxies on the edges of voids seem to be flowing away from their centers, as if fleeing some invisible repulsive force. This void polarization challenges our fundamental models of cosmology and hints at physics beyond our current understanding. Perhaps most unsettling is the void that lies closest to us. The KBC void, an enormous bubble of emptiness spanning nearly 1 billion light-years, with our Milky Way positioned mysteriously near its center. This positioning is so improbable that it threatens the Copernican principle, the fundamental assumption that Earth occupies no special place in the universe. The Big Bang Theory is our current best explanation for how the universe began. It proposes that approximately 13.8 billion years ago, all matter and energy in the cosmos was concentrated into an incredibly dense, hot state. This primordial singularity then rapidly expanded and cooled, giving rise to the vast universe we observe today. This theory doesn't describe an explosion in the conventional sense, but rather a sudden expansion of space itself. As the universe expanded, it cooled enough for subatomic particles to form, which eventually combined into the first atoms. Over billions of years, these atoms clustered together under the influence of gravity, forming stars, galaxies, and the large-scale structures we see in the cosmos. The Big Bang Theory is supported by several key pieces of evidence. One is the cosmic microwave background radiation, a faint glow permeating all of space that represents the leftover heat from the early universe. Another is the observed expansion of the universe, with distant galaxies moving away from us at increasing speeds. Scientists have also found that the abundance of light elements like hydrogen and helium in the universe matches what we would expect if they were created in the intense conditions following the Big Bang. While many questions remain about the exact mechanisms of the early universe, the Big Bang Theory continues to provide a robust framework for understanding cosmic origins. The Big Bang Theory, our current best explanation for the origin of the universe, is supported by several key pieces of evidence. One of the most compelling is the cosmic microwave background radiation, a faint glow of light that fills the entire sky. This ancient light, discovered in 1965, is essentially the afterglow of the Big Bang, providing a snapshot of the universe when it was just 380,000 years old. Another crucial piece of evidence is the abundance of light elements in the universe. The Big Bang theory accurately predicts the amounts of hydrogen, helium, and lithium that we observe in the cosmos. These elements were forged in the intense heat of the early universe, and their proportions align perfectly with what the theory anticipates. The expansion of the universe also strongly supports the Big Bang theory. Observations of distant galaxies show that they are moving away from us, and the farther away they are, the faster they're receding. This expansion is a natural consequence of the Big Bang and was first observed by Edwin Hubble in the 1920s. Lastly, the theory explains the large-scale structure of the universe. The way galaxies are distributed in space, forming clusters and superclusters separated by vast voids, matches what we would expect if the universe began in an extremely hot, dense state and then expanded and cooled over billions of years. These multiple lines of evidence working together provide robust support for the Big Bang theory. The question of what existed before the Big Bang is one of the most profound and challenging in cosmology. Our current understanding of the universe begins with the Big Bang, but the nature of reality prior to this event remains a subject of intense speculation and research. Some theories propose that our universe may have emerged from a pre-existing state, such as a quantum vacuum or a previous cosmic cycle. Others suggest that time itself began with the Big Bang, making the concept of before meaningless in this context. The idea of eternal inflation posits that our universe might be one of many bubbles in an ever-expanding multiverse. It is important to note that our ability to investigate this question is limited by the cosmic horizon, beyond which we cannot observe. The extreme conditions at the beginning of the Big Bang also pose challenges for our current physical theories, which break down at such high energies and densities. As scientists continue to push the boundaries of our knowledge, new theories and observations may shed light on this enigmatic period. For now, the pre-Big Bang era remains one of the greatest mysteries in our quest to understand the cosmos. Scientists employ a variety of sophisticated techniques to study the early moments of the universe. One of the most powerful tools is the analysis of cosmic microwave background radiation, the faint afterglow of the Big Bang that permeates all of space. This ancient light provides a snapshot of the universe when it was just 380,000 years old, allowing researchers to infer conditions in even earlier epochs. Particle accelerators play a crucial role in recreating the extreme conditions that existed in the first fractions of a second after the Big Bang. By colliding particles at nearly the speed of light, scientists can observe how matter behaves at incredibly high energies and temperatures, mimicking the early universe on a small scale. Theoretical physics and advanced mathematical models are essential for understanding the earliest moments of cosmic history. Theories like inflation, which describes an exponential expansion of space in the first instance after the Big Bang, help explain observed features of the universe. Computer simulations based on these models allow scientists to test their predictions against observational data. Astronomical observations of the oldest and most distant objects in the universe, such as ancient galaxies and quasars, provide valuable insights into early cosmic evolution. By studying the light from these distant sources, scientists can piece together the timeline of how the first stars and galaxies formed, illuminating the process of cosmic structure formation in the young universe. Cosmic inflation is a theory that describes an incredibly rapid expansion of the early universe, occurring just a fraction of a second after the Big Bang. This expansion happened faster than the speed of light, causing the universe to grow exponentially in size. During this brief period, the universe expanded by a factor of at least 10 raised to the power of 26 in less than a billionth of a second. This concept was proposed to solve several puzzles about the universe that the standard Big Bang theory couldn't explain. For instance, it addresses why the universe appears so uniform in all directions and why it seems to be geometrically flat. Inflation provides a mechanism for these observations by stretching out any initial irregularities and curvature. Inflation also explains the origin of the large-scale structure we see in the universe today. Quantum fluctuations, Tiny variations in the fabric of spacetime were stretched to cosmic scales during inflation. These fluctuations then became the seeds for the formation of galaxies and galaxy clusters. Relating to the universe's origin, cosmic inflation occurs immediately after the initial singularity of the Big Bang. It sets the stage for the rest of cosmic evolution, creating the vast, expanding universe we observe today. While the exact cause of inflation remains a subject of ongoing research, this theory has become a crucial part of our understanding of the universe's earliest moments and its subsequent development. While the Big Bang theory remains the most widely accepted explanation for the origin of our universe, scientists have proposed several alternative models. One such alternative is the steady-state theory, which suggests that the universe has always existed and continues to expand, with new matter constantly being created to maintain a constant density. Although this theory has fallen out of favor due to observational evidence supporting the Big Bang, it demonstrates the ongoing scientific pursuit of understanding our cosmic origins. Another intriguing alternative is the cyclic model, which proposes that the universe undergoes endless cycles of expansion and contraction. In this scenario, each cycle begins with a big bounce rather than a singular Big Bang event. This theory attempts to address some of the challenges faced by the standard Big Bang model, such as the nature of the initial singularity. The ekpyrotic universe theory presents a different perspective, suggesting that our universe resulted from the collision of two three-dimensional worlds in a higher dimensional space. This model aims to explain the uniformity of the cosmic microwave background radiation without relying on cosmic inflation, a key component of the standard Big Bang theory. These alternative theories, along with others like the string theory-inspired multiverse concept, showcase the dynamic nature of cosmological research. While the Big Bang theory currently provides the best explanation for observed phenomena, scientists continue to explore and refine our understanding of the universe's origins and evolution. Dark energy plays a crucial role in the expansion of our universe, acting as a mysterious force that pushes everything apart. Unlike gravity, which pulls matter together, dark energy exerts a repulsive force that causes the universe to expand at an accelerating rate. Scientists discovered the effects of dark energy by observing distant supernovae, which appeared dimmer than expected. This observation led to the realization that the expansion of the universe was speeding up rather than slowing down as previously thought. Although dark energy makes up about 68% of the universe's total energy and matter, its true nature remains one of the biggest mysteries in modern cosmology. Researchers have proposed various theories to explain dark energy, including the possibility that it is an inherent property of space itself or a new type of dynamic energy field. The presence of dark energy has profound implications for the future of our universe. If it continues to dominate, the universe may expand forever, eventually leading to a cold, dark, and lonely cosmos where stars and galaxies are pushed so far apart that they become invisible to one another. Determining the age of the universe has been a monumental scientific endeavor, relying on multiple lines of evidence and sophisticated observations. One of the primary methods involves measuring the expansion rate of the universe, known as the Hubble constant. By observing distant galaxies and calculating how quickly they are moving away from us, scientists can essentially run the clock backwards to determine when the universe began. Another crucial piece of evidence comes from the cosmic microwave background radiation, the afterglow of the Big Bang. This faint radiation permeates the entire universe and provides a snapshot of the cosmos when it was only about 380,000 years old. By analyzing the patterns and temperature fluctuations in this radiation, researchers can deduce the age and composition of the early universe. The abundance of light elements in the universe, such as hydrogen and helium, also offers clues about its age. The ratio of these elements aligns with predictions of how they would have formed in the first few minutes after the Big Bang. Additionally, the oldest known stars in our galaxy serve as cosmic clocks, providing a minimum age for the universe. Combining these various methods and data from missions like the Planck spacecraft, scientists have refined their estimate of the universe's age. The current best estimate places the age of the universe at approximately 13.8 billion years, with a remarkably small margin of error. This figure represents a triumph of modern cosmology, showcasing our ability to peer back to the very dawn of time and unravel the history of our cosmic home. Cosmic microwave background radiation is the oldest light in the universe, a faint glow that fills all of space. This ancient radiation was emitted about 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form and light to travel freely for the first time. The discovery of this radiation in 1965 provided strong evidence for the Big Bang theory, confirming that the universe had a hot, dense beginning. It acts as a cosmic fossil, preserving information about the early universe and allowing scientists to study conditions that existed billions of years ago. This background radiation is remarkably uniform in all directions, supporting the idea that the universe was smooth and homogeneous in its infancy. However, tiny fluctuations in its temperature reveal the seeds of cosmic structure, the slight irregularities that eventually grew into galaxies and galaxy clusters we see today. By studying the cosmic microwave background, scientists have been able to determine the age, composition, and geometry of the universe with unprecedented precision. It has become an invaluable tool in cosmology, helping to shape our understanding of the universe's history and evolution, and providing insights into fundamental physics on the grandest scales imaginable. The concept of a multiverse is a fascinating idea that has gained traction among some cosmologists and theoretical physicists. This notion suggests that our universe might be just one of many universes existing simultaneously. While we cannot directly observe or prove the existence of other universes, several scientific theories propose their possibility. One such theory stems from the idea of cosmic inflation, which posits that the early universe underwent a period of rapid expansion. This model suggests that quantum fluctuations during this inflationary period could have given rise to multiple universes, each with its own set of physical laws and constants. Another perspective on the multiverse comes from string theory, which attempts to unify different fundamental forces in physics. Some versions of string theory predict the existence of multiple dimensions beyond the four we experience. These extra dimensions could potentially harbor other universes with different properties. It is important to note that the multiverse concept remains speculative and controversial within the scientific community. While it offers intriguing explanations for some cosmological puzzles, such as the fine-tuning of physical constants, it also raises questions about the nature of scientific inquiry and the limits of our ability to test such theories empirically. As our understanding of the cosmos continues to evolve, the idea of a multiverse remains an active area of research and debate. Dark matter is an enigmatic form of matter that does not interact with light or other forms of electromagnetic radiation. Unlike the ordinary matter we can see and touch, dark matter remains invisible and undetectable through conventional means. However, its presence is inferred through its gravitational effects on visible matter, light, and the structure of the universe. Scientists believe dark matter exists due to several compelling observations. Galaxy rotation curves show that galaxies spin faster than they should based on their visible mass alone, suggesting the presence of additional unseen matter. Gravitational lensing, where light from distant objects is bent by massive structures, reveals more mass in galaxy clusters than can be accounted for by visible matter. The formation and distribution of large-scale structures in the universe also point to the existence of dark matter, as ordinary matter alone cannot explain the observed cosmic web of galaxies and galaxy clusters. Furthermore, measurements of the cosmic microwave background radiation, the afterglow of the Big Bang, indicate that ordinary matter makes up only about 5% of the universe's total mass energy content. Dark matter is estimated to comprise about 27%, with the remaining 68% attributed to dark energy, another mysterious component driving the accelerated expansion of the universe. Despite extensive searches, the exact nature of dark matter remains unknown. Leading theories propose various exotic particles, such as weakly interacting massive particles or axions, as potential candidates. Ongoing experiments in particle physics, astrophysics, and cosmology continue to probe the properties of dark matter, aiming to unlock one of the greatest mysteries in modern science. Dark matter was first inferred through astronomical observations rather than directly discovered. In the 1930s, Swiss astronomer Fritz Zwicky studied the Coma cluster of galaxies and noticed something peculiar. The galaxies were moving much faster than expected based on the visible matter alone. Zwicky proposed that some invisible form of matter must be present, providing the extra gravitational force needed to explain the high velocities. This concept remained largely overlooked until the 1970s, when Vera Rubin and Kent Ford made similar observations in individual galaxies. They found that stars at the outer edges of galaxies were orbiting at speeds far too fast for the visible mass to explain. These observations strongly suggested the presence of a large amount of unseen matter extending well beyond the visible boundaries of galaxies. These findings led to the dark matter hypothesis, which proposes that a significant portion of the universe consists of matter that does not interact with light or other forms of electromagnetic radiation. This makes it invisible to our telescopes, but still exerts a gravitational influence on visible matter. Since then, numerous other lines of evidence have supported the existence of dark matter, including gravitational lensing effects, the structure of the cosmic microwave background, and computer simulations of galaxy formation. Despite these indirect observations, the exact nature of dark matter particles remains one of the most intriguing mysteries in modern cosmology. Scientists employ several ingenious methods to detect dark matter despite its elusive nature. One approach involves using large underground detectors filled with substances like liquid xenon or crystals. These detectors are designed to capture the rare interactions between dark matter particles and normal matter, producing tiny flashes of light or heat that sensitive instruments can measure. Another method relies on indirect detection, where scientists search for the products of dark matter annihilation or decay. When dark matter particles collide, they might produce observable particles like gamma rays or neutrinos. Telescopes and specialized detectors scan the sky for these telltale signals, particularly from regions where dark matter is thought to be abundant, such as the centers of galaxies. Particle accelerators offer yet another avenue for dark matter research. By colliding particles at extremely high energies, scientists hope to create dark matter in laboratory conditions. If successful, these experiments could reveal important properties of dark matter particles and help confirm theoretical models. Gravitational lensing provides a powerful tool for mapping dark matter distribution in the universe. As light from distant galaxies passes through regions of space containing dark matter, its path bends, creating distortions in the observed images. By carefully analyzing these distortions, researchers can infer the presence and distribution of dark matter in cosmic structures. Dark matter plays a crucial role in shaping the formation and structure of galaxies, exerting a powerful gravitational influence that goes far beyond what we can see with our telescopes. This invisible substance, which does not interact with light or other forms of electromagnetic radiation, forms the backbone of cosmic structure. In the early universe, dark matter began to clump together under its own gravity, creating a vast cosmic web. These dark matter concentrations acted as gravitational seeds, attracting normal matter to form the first galaxies. As these proto-galaxies grew, the dark matter continued to provide a gravitational scaffold, helping to hold the galaxies together and influencing their rotation. The presence of dark matter explains why galaxies rotate faster than they should based on their visible mass alone. Without dark matter, the outer regions of spiral galaxies would fly apart due to their rapid rotation. Instead, we observe that galaxies are surrounded by massive dark matter halos, extending far beyond their visible boundaries and providing the extra gravitational pull needed to keep stars in their orbits. Dark matter also influences the overall distribution of galaxies in the universe. It forms large-scale structures such as galaxy clusters and cosmic filaments, guiding the placement of galaxies and shaping the cosmic landscape we observe today. By studying these structures, scientists can map the distribution of dark matter and better understand its role in cosmic evolution. Scientists have proposed several intriguing candidates for dark matter particles, each with unique properties that could explain this mysterious substance. One leading contender is the weakly interacting massive particle, often referred to as WIMP. These hypothetical particles would have significant mass, but interact only weakly with ordinary matter, making them difficult to detect directly. Another promising candidate is the axion, a theoretical particle originally proposed to solve a problem in quantum chromodynamics. Axions would be much lighter than WIMPs, but could exist in vast numbers throughout the universe, potentially accounting for the observed effects of dark matter. Sterile neutrinos represent yet another possibility. Unlike the known types of neutrinos, which rarely interact with matter, sterile neutrinos would be even more elusive and could have the right properties to serve as dark matter particles. Some researchers are also exploring more exotic possibilities, such as primordial black holes formed in the early universe or self-interacting dark matter particles that could explain certain observed galactic behaviors. As scientists continue to search for evidence of these particles using advanced detectors and observational techniques, the true nature of dark matter remains one of the most compelling mysteries in modern cosmology. Dark matter remains one of the most enigmatic components of our universe. Unlike regular matter, which we can see and interact with daily, dark matter is invisible and seemingly intangible. It does not emit, absorb, or reflect light, making it incredibly challenging to detect directly. The primary way dark matter interacts with regular matter is through gravity. Its gravitational influence is the reason we know dark matter exists at all. Scientists have observed its effects on the rotation of galaxies, the movement of galaxy clusters, and the bending of light in gravitational lensing. These observations reveal that there must be far more matter in the universe than we can see with our most advanced telescopes. Beyond gravity, dark matter appears to have extremely limited interactions with regular matter. It does not seem to collide with or stick to ordinary particles in any significant way. This lack of interaction allows dark matter to pass through regular matter almost as if it weren't there. Enormous amounts of dark matter likely flow through Earth every second without us noticing. This elusive nature of dark matter poses a significant challenge for scientists attempting to study it. Researchers are developing ever more sensitive detectors, hoping to catch the rare instances when dark matter particles might interact with regular matter in ways we can measure. As our understanding grows, we may uncover new types of interactions between dark and regular matter, potentially revolutionizing our view of the universe. The missing satellite problem is a significant challenge in our understanding of dark matter and galaxy formation. According to current models of cold dark matter, large galaxies like our Milky Way should be surrounded by hundreds or even thousands of smaller satellite galaxies. These satellites would consist of dark matter halos containing varying amounts of visible matter in the form of stars and gas. However, observations have revealed far fewer satellite galaxies than predicted. Around the Milky Way, we have only identified a few dozen satellite galaxies, which is substantially less than what our theories suggest should exist. This discrepancy between the predicted number of satellite galaxies and the observed number is what we call the missing satellite problem. This issue raises important questions about our understanding of dark matter and how galaxies form. Some scientists propose that there might be many more satellite galaxies that are simply too faint for us to detect with current technology. Others suggest that our models of galaxy formation might need revision, particularly in how they describe the behavior of dark matter on smaller scales. The missing satellite problem continues to be an active area of research in astrophysics and cosmology. Scientists are working to refine our observations, improve our theoretical models, and explore new ideas to resolve this discrepancy between theory and observation. As we unravel this mystery, we may gain crucial insights into the nature of dark matter and the processes that shape our universe. Dark matter is intimately connected to the concept of missing mass in the universe. Astronomers first noticed this puzzling discrepancy when studying the rotation of galaxies. They observed that galaxies were spinning much faster than they should be based on the visible matter they contained. This led scientists to realize there must be additional mass present that we cannot see, hence the term missing mass. This invisible substance, which neither emits nor absorbs light, came to be known as dark matter. This invisible substance, which neither emits nor absorbs light, came to be known as dark matter. It interacts with regular matter only through gravity, making it extremely difficult to detect directly. Despite its elusive nature, dark matter plays a crucial role in the structure and evolution of the universe. Scientists estimate that dark matter makes up about 85% of all matter in the universe. This staggering amount accounts for the missing mass needed to explain various cosmic phenomena, such as the formation of galaxies and the large-scale structure of the universe. Without dark matter, the cosmos as we know it simply could not exist. The search for dark matter continues to be one of the most pressing questions in modern astrophysics. As our understanding of this mysterious substance grows, we gain deeper insights into the fundamental nature of our universe and the forces that shape it. Scientists around the world are conducting a variety of experiments in their quest to directly detect dark matter. One of the most prominent approaches involves using large underground detectors filled with ultra-pure materials like xenon or germanium. These detectors are designed to capture the extremely rare interactions between dark matter particles and normal matter. The xenon experiment, located deep beneath a mountain in Italy, uses over 3 tons of liquid xenon to search for these elusive particles. Similarly, the Large Underground Xenon experiment in South Dakota aims to detect dark matter collisions with xenon atoms. These detectors are placed far underground to shield them from cosmic rays and other interference that could mask the faint signals of dark matter. Another method involves using cryogenically cooled crystals. The cryogenic dark matter search, situated in an old iron mine in Minnesota, uses germanium and silicon detectors cooled to near absolute zero. These crystals are so sensitive they can detect the tiniest amounts of energy deposited by a potential dark matter collision. Researchers are also exploring alternative detection methods. The axion dark matter experiment uses powerful magnets to search for axions, hypothetical particles that could explain both dark matter and aspects of nuclear physics. Meanwhile, space-based experiments like the Alpha Magnetic Spectrometer on the International Space Station are looking for indirect evidence of dark matter by measuring cosmic rays and antimatter in space. Dark matter remains one of the most intriguing mysteries in cosmology, and scientists have proposed various theories about its composition. One fascinating possibility is that dark matter could be made up of primordial black holes. These hypothetical objects would have formed in the earliest moments of the universe, long before the first stars ignited. Unlike stellar black holes, which form from the collapse of massive stars, primordial black holes would have been created by the extreme density fluctuations in the very early universe. These fluctuations, caused by quantum effects, could have compressed matter so tightly in some regions that they collapsed into black holes almost immediately after the Big Bang. The idea that primordial black holes could constitute dark matter is appealing for several reasons. They would be massive enough to explain the gravitational effects we observe, yet small and dark enough to have eluded direct detection so far. Additionally, they would not require the existence of new, undiscovered particles beyond the standard model of particle physics. However, this theory faces challenges. Recent observations have placed strict limits on the number of primordial black holes that could exist in certain mass ranges. While these constraints don't completely rule out the possibility, they do make it less likely that primordial black holes could account for all of the dark matter in the universe. Scientists continue to explore this intriguing possibility alongside other dark matter candidates. highlighting the ongoing quest to unravel one of the greatest cosmic enigmas. Dark energy is a mysterious force that permeates all of space and drives the accelerating expansion of our universe. This enigmatic phenomenon counteracts the attractive force of gravity, pushing galaxies apart at an ever-increasing rate. The discovery of dark energy came as a surprise to astronomers in the late 1990s. Two independent teams of scientists were studying distant supernovae, explosive stellar events so bright they can be seen across vast cosmic distances. These researchers expected to find that the expansion of the universe was slowing down due to gravity. Instead, they found something completely unexpected. The expansion was speeding up. This accelerating expansion could only be explained by the presence of an unknown energy source working against gravity on a cosmic scale. This force became known as dark energy. It is called dark because it does not interact with light or other forms of electromagnetic radiation, making it invisible and difficult to study directly. The discovery of dark energy revolutionized our understanding of the cosmos. It showed that the universe is not only expanding, but doing so at an accelerating rate, fundamentally changing our view of the universe's past, present, and future. Today, scientists estimate that dark energy makes up about 68% of the universe, yet its true nature remains one of the biggest mysteries in modern physics. Dark energy is a mysterious force that permeates all of space, pushing the universe apart. Unlike gravity, which pulls matter together, dark energy acts as a cosmic repellent, causing galaxies to move away from each other at an ever-increasing rate. This accelerating expansion was first discovered in the late 1990s when astronomers observed that distant supernovae were fainter than expected. This observation suggested that these exploding stars were farther away than predicted by models of cosmic expansion, indicating that the universe's expansion was speeding up rather than slowing down. Scientists believe dark energy makes up about 68% of the universe's total energy and matter. As the universe expands, the amount of dark energy increases, creating more space between galaxies and galaxy clusters. This process leads to a runaway effect, where the expansion rate continually increases over time. While we can observe the effects of dark energy, its true nature remains one of the biggest mysteries in modern cosmology. Understanding dark energy is crucial for predicting the ultimate fate of our universe, as it will determine whether the cosmos will continue expanding indefinitely or if it might eventually collapse back in on itself. Dark energy remains one of the most perplexing mysteries in modern cosmology. Scientists have proposed several theories to explain this enigmatic force that appears to be accelerating the expansion of our universe. The leading contender is the cosmological constant, an idea originally proposed by Albert Einstein. This theory suggests that dark energy is an inherent property of space itself, with a constant density throughout the cosmos. As the universe expands, more space comes into existence, creating more dark energy and driving further expansion. Another prominent theory is quintessence, which posits that dark energy is a dynamic field that changes over time and space. Unlike the cosmological constant, quintessence could potentially explain why the expansion of the universe seems to be accelerating at different rates throughout cosmic history. Some researchers propose modifications to our understanding of gravity on cosmic scales, suggesting that what we perceive as dark energy might actually be a manifestation of how gravity behaves differently over vast distances. These modified gravity theories aim to explain cosmic acceleration without invoking a new form of energy. Scientists measure the effects of dark energy through several sophisticated methods, each providing a piece of the cosmic puzzle. One primary technique involves observing Type Ia supernovae, which are exploding stars that consistently reach the same peak brightness. By measuring how bright these supernovae appear from Earth, astronomers can determine their distance and calculate how quickly they are moving away from us. This information reveals the expansion rate of the universe at different points in cosmic history, allowing scientists to detect the influence of dark energy. Another crucial approach is the study of the cosmic microwave background radiation, the afterglow of the Big Bang. Scientists analyze tiny fluctuations in this ancient light to understand the universe's early structure and how it has evolved over time. These observations provide valuable insights into the amount of dark energy present in the cosmos and its effects on cosmic expansion. Gravitational lensing, where massive objects bend light from distant sources, also plays a role in dark energy research. By examining how light from faraway galaxies is distorted by intervening matter, scientists can map the distribution of both visible and dark matter in the universe. This information helps constrain models of cosmic structure formation and evolution, which are influenced by dark energy. Large-scale galaxy surveys contribute significantly to our understanding of dark energy as well. By mapping the positions and movements of millions of galaxies, astronomers can detect subtle patterns in cosmic structure that reveal the interplay between gravity and dark energy. These surveys provide a wealth of data that allows scientists to test different models of dark energy and refine our understanding of its properties and effects on the universe's expansion. The cosmological constant is a term in Einstein's equations of general relativity that represents a constant energy density filling all of space. Initially introduced by Einstein to create a static universe model, it was later abandoned when the universe was discovered to be expanding. However, the concept has experienced a revival in modern cosmology. Today, the cosmological constant is closely linked to the phenomenon of dark energy. Dark energy is the mysterious force causing the accelerating expansion of the universe, a discovery that earned the 2011 Nobel Prize in Physics. Scientists propose that the cosmological constant could be the mathematical representation of dark energy in the fabric of space-time. The relationship between the cosmological constant and dark energy lies in their similar effects on the universe. Both concepts describe a form of energy that permeates all of space and exerts a negative pressure, counteracting the attractive force of gravity. This negative pressure is responsible for the observed acceleration in the universe's expansion. While the cosmological constant provides a simple explanation for dark energy, its exact nature remains one of the biggest mysteries in modern physics. Scientists continue to explore alternative theories and conduct observations to better understand this enigmatic force shaping the fate of our universe. Dark energy is a mysterious force that permeates all of space, pushing the universe apart. Its influence on the ultimate fate of the universe is profound and potentially unsettling. As dark energy continues to exert its expansionary pressure, it accelerates the expansion of the cosmos, driving galaxies and galaxy clusters farther apart at an ever-increasing rate. This relentless expansion could lead to what cosmologists call the Big Freeze or heat death scenario. In this potential future, the universe expands so rapidly that eventually galaxies become isolated, unable to see or interact with one another. Stars will exhaust their fuel and die out, leaving behind a cold, dark cosmos populated by black holes, neutron stars, and burned-out stellar remnants. Another possibility is the Big Rip, where the expansion becomes so extreme that it tears apart galaxies, solar systems, planets, and even atoms. This scenario depends on whether dark energy's strength increases over time, a possibility that scientists are still investigating. The nature of dark energy remains one of the biggest mysteries in modern cosmology. Understanding its properties and behavior is crucial for predicting the ultimate fate of our universe. As we continue to study this enigmatic force, we may uncover new possibilities for the cosmic endgame, reshaping our understanding of the universe's destiny. The quintessence theory of dark energy offers an intriguing alternative to the cosmological constant explanation for the accelerating expansion of our universe. This concept proposes that dark energy is not a fixed property of space itself, but rather a dynamic field that permeates the cosmos and changes over time. At its core, quintessence suggests that dark energy is composed of a scalar field, similar to the Higgs field, but with different properties. This field would have its own potential energy and could vary in strength and distribution throughout the universe. Unlike the cosmological constant, which remains uniform, quintessence could potentially clump or form structures on very large scales. One of the most compelling aspects of quintessence is its potential to solve the fine-tuning problem associated with the cosmological constant. The theory allows for the possibility that the energy density of dark energy has evolved over cosmic history, potentially explaining why it appears to be finely tuned to its current value. Quintessence also opens up new avenues for understanding the future of our universe. If this theory proves correct, the fate of the cosmos could be more complex than a simple eternal expansion or Big Rip scenario. The evolving nature of quintessence could lead to periods of accelerated expansion followed by deceleration or even oscillations in the expansion rate of the universe. Dark energy poses a profound challenge to our understanding of physics, pushing the boundaries of our current scientific knowledge. This mysterious force, which appears to be causing the accelerating expansion of the universe, defies explanation within our existing framework of physical laws. One of the most perplexing aspects of dark energy is its apparent uniformity throughout space and time. Unlike other forms of energy we observe, dark energy seems to maintain a constant density as the universe expands. This behavior contradicts our expectations based on known physical principles, where energy typically becomes more diffuse as space expands. The nature of dark energy also raises questions about the fundamental fabric of spacetime. Some theories suggest that dark energy might be an intrinsic property of empty space itself, a concept known as vacuum energy. However, when scientists attempt to calculate the amount of vacuum energy using quantum field theory, the result is wildly different from observations, off by a factor of 10 to the power of 120. This enormous discrepancy between theory and observation highlights the limitations of our current understanding of quantum mechanics and general relativity. Dark energy stands as a cosmic puzzle, urging scientists to develop new theories that can bridge the gap between the very large and the very small, potentially leading to a more comprehensive understanding of the universe and its underlying principles. The existence of dark energy is supported by several key observations that have revolutionized our understanding of the cosmos. One of the most compelling pieces of evidence comes from studying Type Ia supernovae in distant galaxies. These stellar explosions serve as cosmic distance markers, allowing astronomers to measure how quickly the universe is expanding at different points in its history. Observations of these supernovae revealed a surprising fact. The expansion of the universe is accelerating, not slowing down as previously expected. This acceleration requires an unknown force counteracting gravity, which scientists have dubbed dark energy. Another line of evidence comes from the cosmic microwave background radiation, the afterglow of the Big Bang. Detailed measurements of this ancient light reveal the geometry and composition of the early universe. The patterns observed in the cosmic microwave background are consistent with a universe containing a significant amount of dark energy, accounting for about 68% of the total energy content of the cosmos. Large-scale structure surveys, which map out the distribution of galaxies across vast distances, also support the existence of dark energy. These surveys show that the way galaxies cluster together on enormous scales matches predictions from models that include dark energy. Without dark energy, the observed structures would be difficult to explain. Gravitational lensing observations, which detect how light from distant galaxies is bent by the gravity of intervening matter, provide additional evidence. These measurements help constrain the total amount of matter in the universe and indirectly support the need for dark energy to explain the overall composition and behavior of the cosmos. Together, these diverse lines of evidence point to the reality of dark energy, even though its fundamental nature remains one of the biggest mysteries in modern physics. Dark energy remains one of the most perplexing mysteries in modern cosmology. Scientists have indeed proposed that it could be a fundamental property of space itself. This concept aligns with Albert Einstein's idea of the cosmological constant, which he originally introduced to create a static universe model. The notion that dark energy is inherent to space suggests that as the universe expands, it creates more space, and consequently, more dark energy. This would explain the observed acceleration of cosmic expansion. If correct, it means that dark energy is woven into the very fabric of the cosmos, present everywhere and everywhen. This property of space would have profound implications for the fate of our universe. It would mean that the expansion would continue indefinitely, potentially leading to a scenario called the Big Freeze, where the universe becomes increasingly cold and diffuse over vast timescales. However, it is important to note that this is still a hypothesis. Scientists continue to explore alternative explanations for dark energy, including modifications to our understanding of gravity or the existence of unknown fields permeating space. The true nature of dark energy remains an open question, driving ongoing research and exploration in cosmology. Black holes are regions in space where gravity is so intense that nothing, not even light, can escape. They form when massive stars collapse at the end of their lives. As a star runs out of fuel, it can no longer support its own weight. The immense pressure causes the star to implode, compressing all its mass into an incredibly small space. For the most massive stars, this collapse continues until the star's core becomes infinitely dense, creating a singularity. Around this singularity, a boundary forms called the event horizon. Once anything crosses this boundary, it can never escape the black hole's gravitational pull. Black holes come in different sizes. Stellar black holes, formed from collapsed stars, can be several times more massive than our Sun. Supermassive black holes, found at the centers of galaxies, can be millions or billions of times more massive. These cosmic giants likely grew over billions of years by consuming nearby stars and merging with other black holes. Scientists have also discovered evidence of intermediate mass black holes, bridging the gap between stellar and supermassive varieties. These cosmic phenomena continue to fascinate researchers, offering insights into the nature of space, time, and the fundamental laws of our universe. The event horizon of a black hole marks a point of no return, a boundary in space-time where the gravitational pull becomes so intense that nothing, not even light, can escape. As an object approaches this threshold, it experiences extreme gravitational effects. Time begins to slow down dramatically from the perspective of a distant observer, while the object itself undergoes intense stretching and compression. At the event horizon, space becomes severely warped. Matter crossing this boundary is thought to be torn apart by tidal forces, a process colorfully termed spaghettification. The intense gravitational field stretches objects vertically while compressing them horizontally, breaking them down to their fundamental components. Once past the event horizon, the fate of matter and information becomes a subject of intense scientific debate. Some theories suggest that information about the object is preserved on the surface of the event horizon, while others propose that it is irretrievably lost. This conflict between quantum mechanics and general relativity at the event horizon is known as the black hole information paradox. The event horizon also emits a faint glow known as Hawking radiation, named after the physicist Stephen Hawking. This radiation is thought to cause black holes to slowly evaporate over immense timescales, adding another layer of complexity to our understanding of these cosmic enigmas. Black holes are cosmic enigmas that challenge our understanding of physics. Their gravitational pull is so intense that not even light can escape once it crosses the event horizon, the boundary beyond which nothing can return. However, the story doesn't end there. In the 1970s, physicist Stephen Hawking proposed a groundbreaking idea. Black holes might not be entirely black. He suggested that quantum effects near the event horizon could cause black holes to emit a faint glow of radiation, now known as Hawking radiation. This process slowly depletes the mass of the black hole over incredibly long periods of time. While Hawking radiation hasn't been directly observed due to its extremely faint nature, it represents a fascinating intersection of quantum mechanics and general relativity. If this theory holds true, it means that information and energy can indeed escape from a black hole, albeit in a form vastly different from how they entered. Another intriguing phenomenon related to black holes is the concept of gravitational waves. When black holes collide or merge, they send ripples through the fabric of space-time. These gravitational waves carry information about the black holes and their violent interactions, effectively allowing some form of escape from these cosmic monsters. Hawking radiation is a theoretical phenomenon proposed by the renowned physicist Stephen Hawking. It suggests that black holes are not entirely black, but emit a faint glow of particles over time. This concept challenges our traditional understanding of black holes as cosmic entities from which nothing can escape. The process of Hawking radiation occurs at the event horizon, the boundary beyond which nothing can escape a black hole's gravitational pull. According to quantum mechanics, pairs of particles and antiparticles constantly pop into existence in the vacuum of space. Normally, these pairs quickly annihilate each other. However, near a black hole's event horizon, one particle might fall into the black hole while the other escapes, appearing as radiation emitted from the black hole. This emission of particles causes the black hole to lose mass and energy over time. For large black holes, this process is extremely slow, but for smaller black holes, it could lead to eventual evaporation. The smaller the black hole, the faster it radiates and shrinks, potentially ending in a burst of energy. Hawking radiation connects the worlds of quantum mechanics and general relativity, two fundamental theories that have been difficult to reconcile. It provides insights into the nature of black holes and the possibility that information might not be permanently lost when it falls into a black hole, addressing the information paradox that has long puzzled physicists. Supermassive black holes, the colossal cosmic engines at the hearts of galaxies, have long puzzled astronomers with their immense size and power. These behemoths, millions to billions of times more massive than our Sun, form through a complex process that spans billions of years. One leading theory suggests that supermassive black holes begin as smaller seed black holes in the early universe. These seeds might form from the collapse of massive stars or directly from dense clouds of gas. As the young universe evolves, these seed black holes grow by consuming surrounding matter and merging with other black holes during galaxy collisions. Another possibility is that supermassive black holes form from the direct collapse of enormous clouds of gas in the early universe. This process could create black holes with masses of hundreds of thousands of solar masses, providing a substantial head start in their growth. As galaxies form and evolve, their supermassive black holes continue to grow. They feed on gas, dust, and stars that venture too close, increasing in mass and gravitational influence. This growth is often most rapid during periods of intense galactic activity, such as when galaxies collide or when there is an abundance of gas available for consumption. Over billions of years, these processes result in the supermassive black holes we observe today, sitting at the centers of galaxies and profoundly influencing their cosmic neighborhoods. When two black holes collide, it unleashes one of the most powerful and awe-inspiring events in the universe. As these cosmic titans spiral towards each other, they dance a gravitational tango, orbiting faster and faster. Their immense gravitational fields distort space and time around them, sending ripples known as gravitational waves across the fabric of the cosmos. In the final moments before the collision, the black holes move at nearly the speed of light. When they finally merge, a significant portion of their combined mass, often equivalent to several suns, is converted into pure energy. This energy is released in a burst of gravitational waves more powerful than all the light emitted by all the stars in the observable universe. The merger creates a new, more massive black hole that briefly wobbles and rings like a struck bell, sending out gravitational waves at specific frequencies. This ringing quickly subsides as the new black hole settles into a stable state. Meanwhile, any nearby gas or dust is heated to extreme temperatures by the intense gravitational forces, potentially creating a bright flare visible to astronomers. These cosmic collisions provide scientists with valuable data about the nature of gravity, space, and time. By detecting and analyzing the gravitational waves from these events, researchers can test Einstein's theories and gain new insights into the fundamental workings of our universe, opening up an entirely new field of gravitational wave astronomy. Scientists employ a variety of sophisticated techniques to detect and study black holes despite their invisible nature. One primary method involves observing the behavior of nearby stars and gas. As matter falls into a black hole, it forms a swirling disk of material called an accretion disk. This disk becomes superheated, emitting powerful X-rays that can be detected by space-based telescopes. Another crucial approach is the study of gravitational waves. When massive objects like black holes collide, they send ripples through space-time. Advanced detectors on Earth, such as the Laser Interferometer Gravitational Wave Observatory, can measure these minute distortions, providing valuable data about black hole mergers and their properties. However, when we consider what happens to matter and energy that fall into a black hole, we encounter a problem. Stephen Hawking discovered that black holes emit radiation now known as Hawking radiation, which causes them to slowly evaporate over time. This process suggests that black holes will eventually disappear completely. The issue is that this radiation appears to be purely random and contains no information about what fell into the black hole. If a black hole evaporates completely, taking all the information it swallowed with it, this would violate the principles of quantum mechanics. This contradiction between the preservation of information required by quantum mechanics and the apparent loss of information in black holes as described by general relativity is the essence of the information paradox. It has puzzled physicists for decades and continues to be an active area of research, with potential resolutions involving concepts like holography, firewalls, or fundamental revisions to our understanding of space-time at the quantum level. The idea that our universe might exist inside a black hole is a fascinating concept that has intrigued scientists and cosmologists for years. This notion stems from certain similarities between the properties of black holes and the characteristics of our universe. Black holes are incredibly dense regions of space where gravity is so strong that nothing, not even light, can escape once it passes the event horizon. Interestingly, some theories suggest that the extreme conditions inside a black hole could lead to the formation of a new universe. This concept is known as black hole cosmology. One of the key ideas supporting this theory is the similarity between the singularity at the center of a black hole and the singularity thought to have existed at the beginning of our universe, just before the Big Bang. Both involve incredibly dense concentrations of matter and energy. Additionally, the expansion of our universe shares some mathematical similarities with the properties of the event horizon of a black hole. However, it is important to note that this idea remains highly speculative. While it is an intriguing concept that captures the imagination, current scientific observations and our understanding of physics do not provide concrete evidence to support or refute this theory. The nature of black holes and the origins of our universe remain active areas of research in modern cosmology. White holes are theoretical cosmic objects that act as the opposite of black holes. While black holes pull everything in, including light, white holes would theoretically push everything out, expelling matter and energy into space. They represent a solution to Einstein's field equations of general relativity, just as black holes do. The concept of white holes emerged as scientists explored the mathematical descriptions of black holes. In theory, a white hole could be the other end of a black hole, connected by a bridge called a wormhole. This hypothetical structure is sometimes referred to as an Einstein-Rosen bridge. However, unlike black holes, which have been indirectly observed and studied, white holes remain purely theoretical. No evidence for their existence has been found in the observable universe. Some physicists argue that white holes are unlikely to exist in reality because they would be inherently unstable. The relationship between black holes and white holes highlights the complex nature of space-time and the extreme conditions that exist in the universe. While black holes continue to be a subject of intense study and observation, white holes remain an intriguing concept that pushes the boundaries of our understanding of cosmic phenomena. Time is a fundamental dimension of our universe, woven into the very fabric of reality alongside space. It's the measure of change and the sequence of events that allows us to distinguish between past, present, and future. Unlike the spatial dimensions we can easily perceive, time has a unique property. It appears to flow in only one direction. The forward motion of time, often called the arrow of time, is closely linked to a concept in physics known as entropy. Entropy is a measure of disorder in a system, and according to the second law of thermodynamics, the total entropy of an isolated system always increases over time. This means that as time progresses, things naturally tend to become more disordered and spread out. This irreversible increase in entropy gives time its apparent direction. We can break an egg, but we never see a broken egg spontaneously reassemble itself. We remember the past, but not the future. These everyday observations are all manifestations of the arrow of time, driven by the increase in entropy. At the quantum level, time becomes even more perplexing. Some physical processes appear to be reversible, yet we still experience time moving forward. Scientists continue to debate and research why we perceive time as unidirectional when many fundamental laws of physics work equally well forwards and backwards. This ongoing mystery underscores the complex nature of time and its crucial role in shaping our universe and our experience within it. Gravity's influence on time is a fascinating aspect of our universe, revealing the deep connection between space and time. This phenomenon, known as gravitational time dilation, is a key prediction of Einstein's theory of general relativity. The stronger the gravitational field, the slower time passes. On Earth, we experience this effect in subtle ways. Clocks at sea level tick slightly slower than those on mountaintops, where gravity is weaker. The difference is minuscule in our daily lives, but it becomes significant when we consider extreme gravitational environments. Near massive objects like black holes, time slows down dramatically. If you were to observe a clock falling into a black hole, you'd see it tick more slowly as it approaches the event horizon. For the unfortunate clock, time would appear to stop completely at the horizon's edge. This warping of time by gravity isn't just a theoretical concept. It has practical implications for technologies we use every day. Global Positioning System satellites orbiting high above Earth must account for time dilation to provide accurate location data. Without these relativistic corrections, GPS navigation would quickly become useless, drifting by several kilometers each day. Space and time are fundamentally interconnected, forming the fabric of our universe, known as spacetime. This concept, introduced by Albert Einstein in his theory of relativity, revolutionized our understanding of the cosmos. In this framework, space and time are not separate entities, but different aspects of a single continuum. The relationship between space and time is dynamic and flexible. Massive objects like stars and planets warp spacetime, creating what we perceive as gravity. This warping affects not only the path of objects moving through space, but also the flow of time itself. Near very massive objects, time actually passes more slowly compared to regions with less gravitational influence. Moreover, the speed at which an object moves through space affects its journey through time. As an object approaches the speed of light, time for that object slows down relative to a stationary observer. This phenomenon, known as time dilation, has been confirmed through precise measurements using atomic clocks on fast-moving aircraft and satellites. The space-time relationship also manifests in the cosmic speed limit, the speed of light. This universal constant connects space and time, defining the maximum rate at which information or causality can propagate through the universe. This intricate dance between space and time shapes the very nature of reality as we know it, influencing everything from the orbits of planets to the evolution of the cosmos itself. Time travel has long captivated our imagination, and while it remains firmly in the realm of science fiction, Some aspects of it are theoretically possible according to our current understanding of physics. Einstein's theory of special relativity shows that time can flow at different rates for objects moving at different speeds. This effect, known as time dilation, has been proven through experiments with atomic clocks on fast-moving aircraft and satellites. Astronauts on the International Space Station experience time slightly slower than we do on Earth, effectively traveling a tiny bit into the future. Traveling to the past, however, presents far more significant challenges and paradoxes. While some solutions to Einstein's field equations of general relativity suggest the possibility of closed time-like curves, which could theoretically allow for backwards time travel, these solutions require conditions that may not be physically possible, such as the existence of exotic matter with negative energy density. From a practical standpoint, the energy requirements and technological hurdles for any significant time travel are far beyond our current capabilities. While we can't rule out future discoveries that might change our understanding, for now, time travel remains a fascinating subject for speculation and scientific inquiry rather than a practical possibility. The arrow of time is the observed direction of time's flow, always moving forward from the past through the present and into the future. This concept describes our universal experience of time as a one-way street, never reversing or standing still. We see eggs break but never unbreak. We age but never grow younger, and we remember the past but cannot recall the future. This forward march of time exists because of a fundamental principle in physics called entropy. Entropy is a measure of disorder in a system, and according to the second law of thermodynamics, the total entropy of an isolated system always increases over time. This means that systems naturally tend towards greater disorder and less useful energy. The arrow of time is intimately linked to this increase in entropy. As energy spreads out and becomes less concentrated, it creates a distinction between past and future states. The past always has lower entropy than the future, giving time its apparent direction. Interestingly, most laws of physics work equally well forwards and backwards in time. It is only when we consider large systems and the statistical behavior of countless particles that the arrow of time emerges. This connection between the microscopic world of particles and our macroscopic experience of time remains one of the most fascinating aspects of our universe, continually driving scientific inquiry and philosophical debate. Quantum mechanics and relativity present strikingly different perspectives on the nature of time. In quantum mechanics, time is treated as a background parameter, flowing steadily and uniformly. It serves as a framework within which quantum events unfold, but is not directly affected by those events. This view aligns more closely with our everyday experience of time as a constant, unchanging backdrop to the world around us. Relativity, on the other hand, revolutionizes our understanding of time. According to Einstein's theories, time is not absolute, but relative, intimately connected with space in a four-dimensional continuum called spacetime. In relativity, the passage of time can vary depending on an observer's motion or their proximity to massive objects. This leads to phenomena such as time dilation, where time passes more slowly for objects moving at high speeds or in strong gravitational fields. These contrasting treatments of time create a fundamental tension between quantum mechanics and relativity. Quantum theory relies on a fixed, universal time coordinate, while relativity insists that time is flexible and observer-dependent. This discrepancy becomes particularly problematic when trying to reconcile the two theories in extreme conditions, such as the interiors of black holes or the earliest moments of the universe. The quest to resolve this conflict and develop a unified theory of quantum gravity remains one of the greatest challenges in modern physics. Scientists continue to explore various approaches from string theory to loop quantum gravity in their efforts to bridge the gap between these two foundational pillars of physics and achieve a more complete understanding of the nature of time and the universe. The block universe theory proposes that the past, present, and future all exist simultaneously in a four-dimensional block of spacetime. This concept challenges our everyday perception of time as a flowing entity where only the present moment exists. Instead, it suggests that all moments in time are equally real and permanent, much like different locations in space. This theory stems from Einstein's work on special relativity, which showed that the perception of simultaneity can vary for observers in different reference frames. What one person experiences as the present moment might be perceived as the past or future by someone else, depending on their relative motion and position in space. In the block universe model, our experience of time passing is likened to a spotlight moving across a film strip. The entire film exists, but we only perceive the illuminated frame as the present. This challenges our notion of free will and the idea that the future is undetermined, as it suggests that all events, past and future, are already set within this four-dimensional structure. The block universe theory also offers a potential explanation for why time seems to flow in one direction from past to future. It proposes that this apparent flow is a result of our limited perception as three-dimensional beings moving through a four-dimensional reality rather than an inherent property of time itself. Time, a concept that seems so fundamental to our existence, has puzzled philosophers and scientists for centuries. Some theoretical physicists propose that time might not be as absolute or fundamental as we perceive it to be. Instead, they suggest that time could be an emergent property, arising from more basic elements of the universe. This idea challenges our everyday experience of time as a linear progression from past to future. In some theories, time emerges as a result of quantum entanglement between particles. As these particles interact, they create a sequence of events that we interpret as the flow of time. This perspective aligns with the block universe theory, which posits that past, present, and future all exist simultaneously. Other scientists argue that time might be more closely related to the increase of entropy in the universe. As systems become more disordered over time, we perceive this change as the passage of time. This connection between time and entropy could explain why time seems to flow in only one direction, from past to future, aligning with the second law of thermodynamics. While these ideas are still theoretical and hotly debated, they open up fascinating possibilities about the nature of our universe. If time is indeed an emergent property, it could revolutionize our understanding of physics, causality, and even the very fabric of reality itself. As we continue to explore these concepts, we may find that our perception of time is just the tip of a much deeper cosmic iceberg. Near singularities, our understanding of time becomes profoundly challenged. These extreme regions of space-time, such as those found at the center of black holes or potentially at the beginning of the universe, push our physical theories to their limits. As we approach a singularity, the intense gravitational effects cause time to slow down dramatically from an outside observer's perspective. However, for someone falling into a black hole, time would appear to progress normally, while the outside universe would seem to speed up. The concept of time as we know it may cease to have meaning altogether at the singularity itself. Our current physical models, including general relativity, break down under these extreme conditions. The immense curvature of space-time near a singularity could potentially cause time and space to become indistinguishable, erasing the distinction between past, present, and future. Some theories suggest that quantum effects might prevent true singularities from forming, replacing them with extremely dense but finite regions where space-time takes on a foam-like structure at the smallest scales. In this scenario, time could become quantized, existing in discrete units rather than as a continuous flow. The breakdown of time near singularities highlights the limits of our current understanding of the universe. It points to the need for a more comprehensive theory that can unite general relativity with quantum mechanics, potentially revealing new insights into the nature of time itself in these extreme environments. Quantum entanglement is a fascinating phenomenon in the subatomic world where two particles become intrinsically linked regardless of the distance between them. When particles are entangled, the quantum state of each particle cannot be described independently, even when separated by vast distances. This means that measuring one particle instantly affects its entangled partner, seemingly defying the speed of light. This bizarre behavior challenges our understanding of time in several ways. First, it suggests that information between entangled particles travels instantaneously, faster than light, which contradicts Einstein's theory of special relativity. This apparent violation of causality raises questions about the nature of time itself and whether our conventional understanding of cause and effect applies at the quantum level. Furthermore, quantum entanglement experiments have shown that the order of measurements on entangled particles does not matter, even when those measurements are separated in time. This implies that quantum correlations can reach backwards and forwards in time, blurring the distinction between past, present, and future. Some physicists propose that quantum entanglement might indicate that time is not a fundamental aspect of reality, but emerges from deeper quantum processes. This idea challenges our intuitive understanding of time as a linear progression and suggests that at the most fundamental level, all moments might exist simultaneously in a timeless quantum realm. The Fermi paradox is a thought-provoking concept in the field of astrobiology and the search for extraterrestrial intelligence. It addresses the apparent contradiction between the high probability of alien civilizations existing in our vast universe and the lack of evidence for or contact with such civilizations. Named after the renowned physicist Enrico Fermi, this paradox emerged from a simple question he posed: where is everybody? Given the age and size of the universe, with its billions of galaxies and even more planets, it seems statistically likely that intelligent life should have evolved elsewhere. If such civilizations exist, some should have developed interstellar travel capabilities and spread throughout the galaxy. Yet despite our ongoing search, we have found no conclusive evidence of extraterrestrial intelligence. This absence of contact or signs of alien civilizations is what makes the Fermi paradox so intriguing. It challenges our understanding of the universe and raises questions about the nature of intelligent life, technological development, and the potential barriers to interstellar communication and exploration. The Fermi paradox has led scientists and thinkers to propose various explanations, ranging from the rarity of life-supporting conditions to the possibility that advanced civilizations destroy themselves before achieving interstellar travel. These proposed solutions continue to fuel scientific inquiry and philosophical debates about our place in the cosmos. Scientists believe intelligent life should be common in the universe due to several compelling factors. First, the sheer vastness of the cosmos provides an astronomical number of potential habitats. Our galaxy alone contains hundreds of billions of stars, and the observable universe houses trillions of galaxies. This immense scale suggests countless opportunities for life to emerge and evolve. Furthermore, the discovery of exoplanets has revealed that planets are not rare cosmic oddities, but rather common features of star systems. Many of these worlds exist in the habitable zone of their stars, where conditions could support liquid water on their surfaces. This abundance of potentially life-friendly environments strengthens the case for widespread intelligent life. The rapid emergence of life on Earth, appearing relatively soon after the planet's formation, indicates that life might arise quickly given the right conditions. Additionally, the principle of mediocrity suggests that Earth and its life forms are not exceptional, implying that similar processes could occur elsewhere. Lastly, the diversity and adaptability of life on Earth demonstrate its resilience and ability to thrive in various environments. This adaptability, combined with the age of the universe, provides ample time and opportunity for intelligence to develop in numerous locations across the cosmos. The Fermi paradox, named after physicist Enrico Fermi, poses a perplexing question. If the universe is so vast and old, why haven't we encountered evidence of extraterrestrial civilizations? Scientists and thinkers have proposed numerous solutions to this enigma, each offering a unique perspective on our cosmic solitude. One prominent explanation is the Great Filter hypothesis. This theory suggests that there might be an insurmountable obstacle preventing life from evolving into advanced civilizations capable of interstellar travel. This filter could be a challenging step in evolution, a tendency for intelligent species to destroy themselves, or an as yet unknown cosmic event that regularly wipes out complex life. Another intriguing proposal is the zoo hypothesis. This idea posits that advanced alien civilizations are aware of us but choose not to make contact, observing Earth as if it were a cosmic zoo. They might be waiting for humanity to reach a certain level of technological or social development before initiating contact, preserving our natural evolution in the meantime. The rare Earth hypothesis offers a different view, suggesting that the conditions necessary for complex life are exceptionally uncommon in the universe. This theory argues that the precise combination of factors that allowed life to flourish on Earth might be extraordinarily rare, making our planet a cosmic oasis in an otherwise barren universe. The Drake equation and the Fermi paradox are closely intertwined concepts in the search for extraterrestrial intelligence. The Drake equation, formulated by astronomer Frank Drake, attempts to estimate the number of detectable civilizations in our galaxy. It considers factors such as the rate of star formation, the fraction of stars with planets, and the likelihood of intelligent life emerging and developing technology. On the surface, the Drake equation often yields optimistic results, suggesting that there could be numerous advanced civilizations in the Milky Way. However, this leads us directly to the Fermi paradox, named after physicist Enrico Fermi. The paradox asks a simple yet profound question. If there are so many potential alien civilizations out there, why have we not detected any signs of their existence? This apparent contradiction between the Drake equation predictions and the lack of observable evidence for extraterrestrial intelligence forms the core of the Fermi paradox. The equation suggests abundance, while our observations indicate absence. This disconnect has led scientists to propose various explanations, ranging from the rarity of life emerging to the possibility that advanced civilizations tend to destroy themselves or choose not to communicate. The relationship between these two concepts continues to drive research and speculation in the field of astrobiology. Scientists refine the parameters of the Drake equation while also developing new search strategies to address the Fermi paradox, constantly pushing the boundaries of our understanding of life in the universe. The Great Filter Hypothesis is a thought-provoking concept in the field of astrobiology and the search for extraterrestrial intelligence. It attempts to explain why we have not yet discovered any signs of advanced alien civilizations, despite the vast number of potentially habitable planets in our galaxy. This hypothesis suggests that there are certain developmental stages or hurdles that a species must overcome to become a spacefaring civilization capable of colonizing other worlds. These stages could include the emergence of life, the evolution of complex organisms, the development of intelligence, and the creation of advanced technology. The Great Filter proposes that one or more of these stages are extremely difficult to pass, acting as a filter that prevents most life forms from reaching interstellar capabilities. If the Great Filter lies in our past, it means humanity has already overcome the most challenging obstacles. This could explain why we have not encountered other civilizations, as they may not have made it through the same hurdles. However, if the Great Filter lies in our future, it suggests that there might be some catastrophic event or challenge ahead that most advanced civilizations fail to survive, such as self-destruction through nuclear war, climate change, or unforeseen consequences of technological advancement. The Great Filter hypothesis has significant implications for our understanding of life in the universe and our own future as a species. It encourages us to consider both the rarity of intelligent life and the potential challenges we may face as we continue to advance technologically and explore the cosmos. The possibility of advanced civilizations concealing their existence from us is a fascinating concept in the search for extraterrestrial intelligence. This idea, known as the zoo hypothesis, suggests that alien civilizations might be observing Earth from afar, deliberately avoiding contact with our young and developing species. There are several reasons why advanced civilizations might choose to remain hidden. They could be protecting us from potentially harmful knowledge or technology that our society is not yet ready to handle. Alternatively, they might be conducting long-term scientific studies, observing our natural development without interference, much like how we study wildlife in nature preserves. Another possibility is that these civilizations have developed stealth technologies far beyond our current understanding, allowing them to mask their presence from our detection methods. They might have found ways to conceal their radio emissions, shield their planets, or even manipulate space-time to avoid detection. However, it is important to note that this remains speculative. The vastness of the universe and the limitations of our current technology make it challenging to confirm or deny the existence of hidden civilizations. The search for extraterrestrial intelligence continues, and future advancements may yet reveal what, if anything, might be concealed from our view. Interstellar travel constraints play a significant role in shaping our understanding of the Fermi paradox. The vast distances between stars pose formidable challenges for any civilization attempting to explore or colonize the galaxy. Even at speeds approaching that of light, which are currently far beyond our technological capabilities, journeys between neighboring star systems would take years, if not decades. These immense travel times introduce numerous complications. Spacecraft would need to be entirely self-sufficient for extended periods, capable of sustaining crew or automated systems for generations. The energy requirements for accelerating to relativistic speeds and then decelerating at the destination are enormous, far exceeding our current energy production capabilities. Moreover, the challenges of navigation and communication across interstellar distances are daunting. The precision required to hit a target light years away is extreme, and communication delays would make real-time interaction with the homeworld impossible. These factors could significantly limit the ability of any civilization to spread across the galaxy, potentially explaining why we have not detected signs of extraterrestrial intelligence despite the apparent abundance of habitable planets. However, the constraints of interstellar travel might also suggest alternative explanations for the Fermi paradox. Advanced civilizations might opt for more efficient means of exploration, such as self-replicating probes or advanced telescopes, rather than physical travel. They might also choose to focus on virtual or simulated experiences rather than physical expansion, or develop technologies that transcend our current understanding of physics and space-time. The age of the universe is a crucial factor in the Fermi paradox, which questions why we haven't detected signs of extraterrestrial civilizations despite the vast number of stars and potential planets in our galaxy. Our universe is approximately 13.8 billion years old, providing ample time for life to emerge and evolve on countless worlds. This immense age suggests that if intelligent life is common, some civilizations could have had billions of years to develop advanced technologies and spread across the galaxy. Even with slower-than-light travel, a determined species could theoretically colonize the entire Milky Way within a few million years, a mere blink in cosmic timescales. The fact that we don't see evidence of such widespread colonization or detect any clear signs of intelligent life raises intriguing questions. Are we truly alone? Or are there fundamental limitations to interstellar travel and communication that we don't yet understand? The age of the universe amplifies these questions, as it seems to provide more than enough time for detectable civilizations to arise. Moreover, the universe's age also relates to the development of elements necessary for life as we know it. The earliest stars forged heavier elements through nuclear fusion, and subsequent generations of stars further enriched the cosmos with complex atoms. This process, occurring over billions of years, created the conditions for life to emerge, adding another layer to the puzzle of why we seem to be alone in this ancient and element-rich universe. The search for extraterrestrial intelligence involves a multifaceted approach combining astronomy, technology, and innovative thinking. One primary method is radio astronomy, where scientists use massive radio telescopes to scan the cosmos for artificial signals that might indicate intelligent communication. These telescopes, like the Allen Telescope Array in California, listen for narrow-band radio emissions that stand out from natural cosmic background noise. Optical searches also play a crucial role. Astronomers look for brief, intense flashes of light that could signify laser communications from advanced civilizations. Additionally, researchers analyze the light from distant stars for signs of megastructures, such as hypothetical Dyson spheres, which could indicate the presence of highly advanced alien societies. Exoplanet studies contribute significantly to this search. As we discover and analyze planets orbiting other stars, scientists look for biosignatures in their atmospheres. These chemical markers could reveal the presence of life, potentially leading us to intelligent civilizations. The search extends to our own solar system, with missions to Mars and the moons of Jupiter and Saturn looking for microbial life, which could provide clues about the potential for intelligence elsewhere. Cutting-edge projects are expanding our search capabilities. The Breakthrough Listen initiative, for example, employs powerful computers to analyze vast amounts of data from telescopes worldwide, searching for patterns that might reveal extraterrestrial technologies. As our methods and technologies advance, we continue to push the boundaries of our cosmic exploration, driven by the profound question: are we alone in the universe? The question of whether we are alone in the universe is one of the most profound and enduring mysteries in science. Given the vastness of the cosmos, with its billions of galaxies each containing billions of stars, the possibility that Earth is the only planet harboring life seems increasingly unlikely. However, the fact remains that we have not yet discovered definitive evidence of life beyond our world. If we are indeed alone, it would suggest that the emergence of life, particularly complex and intelligent life, is an incredibly rare and perhaps even unique occurrence. This scenario, often referred to as the rare Earth hypothesis, proposes that the specific conditions necessary for life as we know it are exceptionally uncommon. These conditions include factors such as the right distance from a stable star, a protective magnetic field, and a large moon to stabilize the planet's axis. The implications of being alone in the universe would be profound. It would mean that humanity bears an immense responsibility as the sole custodians of consciousness and intelligence in the cosmos. Our planet would be not just rare, but unique, making the preservation of Earth and its ecosystems paramount. The loneliness of our existence might also drive us to explore and potentially colonize other worlds, ensuring the continuation of life beyond our home planet. However, it is crucial to note that our search for extraterrestrial life is still in its infancy. We have only begun to scratch the surface of our own solar system, let alone the countless other star systems in our galaxy. As our technology advances and our understanding of the universe deepens, we may yet discover that we are not alone after all, fundamentally altering our perspective on our place in the cosmos. Quantum entanglement is a fascinating phenomenon that occurs at the smallest scales of our universe. It describes a unique connection between particles that allows them to instantly influence each other, regardless of the distance between them. This bizarre behavior challenges our everyday understanding of how the world works. When particles become entangled, their quantum states are linked in such a way that measuring one particle immediately affects its partner. This connection is so strong that Albert Einstein famously referred to it as spooky action at a distance. He found it difficult to accept that information could seemingly travel faster than light. Scientists have conducted numerous experiments to confirm the reality of quantum entanglement. These tests have shown that entangled particles can indeed influence each other instantaneously, even when separated by vast distances. This discovery has profound implications for our understanding of the nature of reality and the fundamental principles of quantum mechanics. Quantum entanglement is not just a curiosity of the subatomic world. It has practical applications in fields such as quantum computing, cryptography, and teleportation of quantum information. As we continue to explore this strange quantum realm, we may uncover even more surprising revelations about the fabric of our universe. Quantum entanglement is a phenomenon that defies our everyday understanding of how the world works. It occurs when two particles become inextricably linked, so that the quantum state of each particle cannot be described independently, even when the particles are separated by a large distance. This bizarre connection seems to violate a fundamental principle of physics, that information cannot travel faster than the speed of light. When we measure one entangled particle, we instantly know the state of its partner, regardless of how far apart they are. This instantaneous connection appears to suggest that information is being transmitted faster than light, which contradicts Einstein's theory of special relativity. However, scientists have shown that no actual information is being sent, preserving the cosmic speed limit. The implications of quantum entanglement extend beyond just particle physics. It challenges our notions of locality and realism, suggesting that the universe might be more interconnected than we previously thought. Some interpretations even propose that entanglement implies the existence of multiple universes, or that reality only takes shape when we observe it. These mind-bending concepts force us to question our understanding of space, time, and the nature of reality itself. As we continue to explore quantum entanglement, we may need to radically reshape our view of the universe and our place within it. The Einstein-Podolsky-Rosen paradox, often called the EPR paradox, is a thought experiment that challenges our understanding of quantum mechanics. It was proposed by Albert Einstein, Boris Podolsky, and Nathan Rosen in 1935 as a way to question the completeness of quantum theory. At its core, the EPR paradox deals with the concept of quantum entanglement. This phenomenon occurs when two particles become connected in such a way that the quantum state of each particle cannot be described independently, even when separated by large distances. The paradox arises from the apparent conflict between quantum mechanics and the principle of local realism, which suggests that objects have definite properties whether or not they are measured, and that no information can travel faster than the speed of light. According to quantum mechanics, measuring one particle of an entangled pair instantly affects the state of its partner, regardless of the distance between them. This seemingly instantaneous action at a distance troubled Einstein and his colleagues, as it appeared to violate the principle of locality in special relativity. They argued that quantum mechanics must be incomplete, as it could not account for this apparent faster-than-light communication. The EPR paradox has led to decades of debate and research in quantum physics. It has spurred the development of new experiments and theories, including Bell's theorem and quantum teleportation. While many physicists now accept the reality of quantum entanglement, the EPR paradox continues to challenge our intuitions about the nature of reality and the foundations of quantum mechanics. Quantum entanglement, one of the most perplexing phenomena in physics, has been experimentally verified through a series of increasingly sophisticated tests over the past few decades. Scientists have used a variety of methods to create and measure entangled particles, providing strong evidence for this counterintuitive quantum behavior. One of the most famous experiments involves the use of entangled photons. Researchers generate pairs of photons with correlated properties, such as polarization, and then separate them over large distances. By measuring the properties of one photon, they can instantly determine the properties of its entangled partner, even when the particles are far apart. This seemingly instantaneous communication between particles has been observed over distances of hundreds of kilometers. Another crucial experiment in verifying quantum entanglement is the violation of Bell's inequalities. These mathematical relations, proposed by physicist John Bell, set limits on the correlations between particles in classical physics. Experiments have consistently shown that entangled particles violate these inequalities, demonstrating behavior that cannot be explained by classical physics alone. More recently, scientists have achieved entanglement between larger objects, such as atoms and even small mechanical oscillators. These experiments push the boundaries of quantum mechanics and help bridge the gap between the quantum and macroscopic worlds, further confirming the reality of quantum entanglement and its potential applications in fields like quantum computing and secure communication. Quantum teleportation is a remarkable process that allows the precise transfer of quantum information from one location to another without physically moving the particle itself. This phenomenon relies on the strange and counterintuitive principles of quantum mechanics, particularly the concept of quantum entanglement. The process begins with two particles that are quantum entangled, meaning their quantum states are inextricably linked regardless of the distance between them. These entangled particles are separated, with one sent to the sender and the other to the receiver. The sender then interacts the particle to be teleported with their half of the entangled pair and performs a measurement. This measurement destroys the quantum state of the original particle, but provides crucial information about its state. The sender then transmits this measurement information to the receiver through classical communication channels. Using this information, the receiver can manipulate their half of the entangled pair to recreate the exact quantum state of the original particle. The quantum information has been teleported from the sender to the receiver without the physical transfer of the particle itself. It is important to note that quantum teleportation does not involve the instantaneous transfer of matter or energy faster than the speed of light. Instead, it is the quantum information that is teleported, and this process still requires classical communication to complete the transfer. This fascinating technique has potential applications in quantum computing and secure communication networks, pushing the boundaries of our understanding of the quantum world. Quantum entanglement, a phenomenon where particles become inextricably linked, holds immense potential for future technologies. This strange quantum effect could revolutionize various fields, from computing to communication. In the realm of computing, quantum entanglement is key to developing powerful quantum computers. These machines could solve complex problems exponentially faster than classical computers, potentially transforming fields like drug discovery, financial modeling, and climate prediction. Quantum entanglement also promises to enhance communication security. Quantum key distribution systems use entangled particles to create unbreakable encryption keys. Any attempt to intercept the communication would disrupt the entanglement, alerting users to potential eavesdropping. Moreover, quantum entanglement could lead to ultra-precise sensors. Entangled particles could be used to create extremely sensitive magnetometers or gravimeters, enabling more accurate navigation systems, improved medical imaging, and even the detection of underground resources or hidden structures. Non-locality in quantum mechanics challenges our everyday understanding of the physical world. This principle suggests that particles can instantaneously influence each other, regardless of the distance between them. It defies our classical intuition, where we expect interactions to be limited by the speed of light. At the heart of non-locality is the phenomenon of quantum entanglement. When two particles become entangled, their quantum states are linked in such a way that measuring one particle immediately affects the state of the other. This connection persists even if the particles are separated by vast distances, such as opposite ends of the universe. Albert Einstein famously referred to this phenomenon as spooky action at a distance, as it seemed to violate his theory of special relativity. However, numerous experiments have confirmed the reality of non-locality, forcing scientists to reconsider our fundamental understanding of space, time, and causality. Non-locality has profound implications for our understanding of the universe. It suggests that at the quantum level, the universe is more interconnected than we previously thought, with information potentially able to travel faster than light. This principle continues to puzzle physicists and philosophers alike, highlighting the mysterious and counterintuitive nature of the quantum world. Quantum entanglement and consciousness are two of the most perplexing phenomena in science, and their potential connection has intrigued researchers for decades. Quantum entanglement occurs when particles become interconnected in such a way that the quantum state of each particle cannot be described independently, even when separated by vast distances. This mysterious link between particles has led some scientists to speculate about its role in the equally enigmatic realm of consciousness. One theory proposes that quantum processes within the brain might play a crucial role in generating consciousness. Proponents argue that the complex network of neurons in our brains could potentially sustain quantum effects, allowing for the kind of instantaneous information transfer and processing that might explain the unified nature of conscious experience. However, it is important to note that this idea remains highly speculative and controversial within the scientific community. Critics of this hypothesis point out that the warm, wet environment of the brain would likely cause quantum effects to decohere too quickly to be relevant for consciousness. They argue that classical physics and neurobiology are sufficient to explain the workings of the mind. Nevertheless, ongoing research continues to explore the potential links between quantum mechanics and consciousness, pushing the boundaries of our understanding in both fields. While the relationship between quantum entanglement and consciousness remains uncertain, the exploration of this connection highlights the fascinating intersections between physics, neuroscience, and philosophy. As our knowledge of both quantum mechanics and the brain expands, we may uncover new insights into the nature of reality and our place within it. Quantum entanglement holds immense potential for revolutionizing computing. This strange quantum phenomenon, where particles become inextricably linked regardless of distance, could enable unprecedented computational power and security. One of the most promising applications is in quantum computing. By harnessing entangled particles, quantum computers could perform complex calculations exponentially faster than classical computers. This could lead to breakthroughs in fields such as drug discovery, financial modeling, and climate prediction, tackling problems that are currently unsolvable with traditional computing methods. Quantum entanglement also forms the basis for quantum cryptography, a potentially unbreakable method of secure communication. Any attempt to intercept or measure the entangled particles would disrupt their delicate quantum state, immediately alerting the communicating parties to the breach. This could provide a level of security that surpasses any classical encryption technique. Another exciting application is quantum teleportation, which could enable the instantaneous transfer of quantum information over vast distances. While this does not involve the physical teleportation of matter, it could be crucial for creating quantum networks and eventually a quantum internet. Such a network could revolutionize data transmission, offering unprecedented speed and security for global communications. Quantum entanglement is a fascinating phenomenon in the realm of quantum physics, where particles become interconnected in such a way that the quantum state of each particle cannot be described independently. However, it is important to clarify that there is no scientific evidence linking quantum entanglement to telepathy or other paranormal claims. While quantum entanglement allows for instantaneous correlation between entangled particles, even across vast distances, this does not translate to the transfer of information faster than the speed of light. The principles of quantum mechanics operate on subatomic scales and do not directly apply to the macroscopic world of human consciousness or communication. Scientists have conducted numerous experiments to test claims of telepathy and other paranormal phenomena, but none have produced reliable, reproducible results that would support these ideas. The current scientific consensus is that telepathy and similar claims are not supported by empirical evidence. It is natural for people to seek explanations for unusual experiences, and quantum mechanics can seem mysterious and potentially applicable to unexplained phenomena. However, it is crucial to rely on rigorous scientific methods and evidence when evaluating such claims, rather than extrapolating quantum effects to unrelated domains. The measurement problem in quantum mechanics is a fundamental challenge that has puzzled scientists for decades. At its core, this problem arises from the stark difference between what quantum theory predicts and what we actually observe in the real world. Quantum mechanics tells us that particles can exist in multiple states simultaneously, a phenomenon known as superposition. For instance, an electron might be spinning both clockwise and counterclockwise at the same time. However, when we measure the electron's spin, we always find it in one definite state, either clockwise or counterclockwise, never both. This sudden change from multiple possibilities to a single reality is called the collapse of the wave function. The measurement problem asks why and how this collapse occurs. It questions whether our act of measurement somehow forces the quantum system to choose a single state, or if there is some hidden mechanism at work that we do not yet understand. Various interpretations of quantum mechanics have been proposed to address this problem, including the many worlds interpretation and the Copenhagen interpretation. However, despite decades of research and debate, the measurement problem remains one of the most intriguing and contentious issues in modern physics, challenging our understanding of reality at its most fundamental level. Observation plays a crucial role in quantum systems, fundamentally altering the behavior of particles at the subatomic level. When we observe a quantum system, we inevitably interact with it, causing what physicists call wave function collapse. This phenomenon transforms the quantum state from a superposition of possibilities into a single, definite outcome. Before observation, quantum particles exist in a state of probability, described by wave functions that represent all potential states simultaneously. This is famously illustrated by the thought experiment of Schrödinger's cat, where a hypothetical cat in a box is both alive and dead until observed. Similarly, quantum particles can occupy multiple positions or have various properties at once. The act of measurement forces the quantum system to choose one of these potential states. This is not merely a matter of uncovering pre-existing information, but actually influences the system itself. The observer effect in quantum mechanics goes beyond the classical idea of measurement disturbing a system. It fundamentally shapes reality at the quantum level. This principle has profound implications for our understanding of reality and the nature of existence. It suggests that the universe is not deterministic at its smallest scales, and that consciousness, through the act of observation, plays an active role in shaping the physical world around us. This interplay between observer and observed continues to be a subject of intense study and debate in the field of quantum physics. Wave function collapse is a fundamental concept in quantum mechanics that describes what happens when we observe or measure a quantum system. Before measurement, a quantum system exists in a superposition of multiple possible states, described by its wave function. This wave function represents all the potential outcomes of a measurement. However, when we actually perform a measurement, the system appears to instantly collapse into one definite state. The controversy surrounding wave function collapse stems from its seemingly paradoxical nature and the questions it raises about the nature of reality. Some scientists argue that the collapse is a real, physical process that occurs when a quantum system interacts with a classical measuring device. Others contend that it is merely a mathematical description of our changing knowledge about the system rather than a physical event. This debate touches on deep philosophical questions about the role of consciousness in quantum mechanics and the nature of measurement itself. Some interpretations, like the Copenhagen interpretation, accept wave function collapse as a fundamental feature of quantum mechanics. Others, such as the many worlds interpretation, argue that the wave function never actually collapses, but instead splits into multiple parallel universes. The controversy is further fueled by the fact that we cannot directly observe the collapse process itself. This leaves room for various interpretations and has led to ongoing debates about the true nature of quantum reality. Despite decades of research and discussion, there is still no consensus among physicists about how to resolve these fundamental questions about wave function collapse and its implications for our understanding of the universe. The Copenhagen interpretation of quantum mechanics is a foundational perspective on how we understand the behavior of particles at the quantum level. Developed primarily by physicists Niels Bohr and Werner Heisenberg in the 1920s, this interpretation addresses the peculiar and often counterintuitive nature of quantum phenomena. At its core, the Copenhagen interpretation posits that quantum systems exist in a state of superposition, where multiple potential outcomes coexist simultaneously. This superposition only collapses into a definite state when an observation or measurement is made. This concept challenges our classical understanding of reality, suggesting that the act of measurement itself plays a crucial role in determining the outcome of quantum events. One of the key principles of the Copenhagen interpretation is the idea of wave function collapse. Before measurement, a quantum system is described by a wave function that represents all possible states. Upon observation, this wave function instantaneously collapses, yielding a single definite result. This interpretation also emphasizes the inherent probabilistic nature of quantum mechanics, asserting that we can only predict the likelihood of various outcomes rather than determine them with certainty. The Copenhagen interpretation has profound implications for our understanding of reality. It suggests that the quantum world is fundamentally indeterminate and that our classical notions of causality and determinism break down at the quantum scale. This perspective has sparked decades of debate and continues to influence how scientists approach the mysteries of the quantum realm. The many worlds interpretation offers a bold solution to the measurement problem in quantum mechanics. This theory, proposed by Hugh Everett in the 1950s, suggests that every time a quantum measurement occurs, the universe splits into multiple parallel realities. Each of these realities corresponds to one possible outcome of the measurement. In the conventional Copenhagen interpretation, a quantum system exists in a superposition of states until it is observed, at which point the wave function collapses into a single definite state. The many worlds interpretation eliminates this collapse entirely. Instead, it posits that all possible outcomes of a measurement actually occur, but in different parallel universes. This approach addresses the measurement problem by removing the need for a special measurement process or observer. In the many worlds view, the act of measurement simply causes the observer to become entangled with the system being measured, creating multiple versions of the observer, each experiencing a different outcome. This eliminates the arbitrary distinction between the quantum and classical worlds that troubles other interpretations. Critics of the many worlds interpretation often find it difficult to accept the existence of countless parallel universes that are unobservable to us. However, proponents argue that it provides a more consistent and universal description of quantum mechanics, avoiding the need for ad hoc rules about measurement and collapse. The debate continues, highlighting the ongoing challenge of reconciling quantum theory with our everyday experience of the world. Quantum decoherence is a fundamental process in quantum mechanics that explains how quantum systems lose their delicate superposition states when they interact with their environment. This phenomenon occurs when the quantum wave function of a system becomes entangled with its surroundings, causing the quantum information to spread out and become effectively classical. The measurement problem in quantum mechanics refers to the puzzling question of why we observe definite outcomes in measurements, despite quantum theory suggesting that particles can exist in multiple states simultaneously. Quantum decoherence provides a crucial link between these seemingly contradictory aspects of quantum theory and our everyday classical experiences. As quantum systems interact with their environment, information about their quantum states leaks out, leading to a loss of quantum coherence. This process happens incredibly quickly for larger objects, explaining why we do not observe quantum superpositions in our everyday world. Decoherence effectively selects preferred states that are stable against environmental interactions, which align with the classical properties we observe. While quantum decoherence does not completely solve the measurement problem, it offers valuable insights into the transition from quantum to classical behavior. It helps explain why macroscopic objects behave classically and why certain quantum states are more likely to be observed than others, bridging the gap between the strange quantum world and our familiar classical reality. The measurement problem in quantum mechanics poses a profound challenge to our understanding of reality. At its core, this issue revolves around the peculiar behavior of quantum systems before and after measurement. In the quantum world, particles exist in a state of superposition, occupying multiple states simultaneously. However, when we observe or measure these particles, they suddenly snap into a definite state. This phenomenon raises perplexing questions about the nature of reality. Is the act of measurement itself causing the particle to choose a state? Or does the particle exist in all possible states until observed? These questions strike at the heart of what we consider real and observable in our universe. The implications of the measurement problem extend beyond the realm of subatomic particles. It suggests that our very act of observing might be influencing the outcome of experiments, blurring the line between observer and observed. This challenges the traditional notion of an objective reality existing independently of our observations. Furthermore, the measurement problem highlights the limitations of our current understanding of quantum mechanics. Despite its remarkable predictive power, the theory struggles to explain why and how the act of measurement causes this apparent collapse of possibilities into a single reality. This gap in our knowledge continues to fuel debates among physicists and philosophers, pushing us to reconsider our most fundamental assumptions about the nature of existence and our place in the cosmos. Consciousness plays a fascinating and controversial role in some interpretations of quantum mechanics, particularly when it comes to the measurement problem. This idea, often associated with the Copenhagen interpretation, suggests that conscious observation might be necessary to collapse the wave function and determine the outcome of quantum measurements. According to this view, quantum systems exist in a superposition of multiple states until they are observed or measured by a conscious entity. At that point, the act of observation causes the wave function to collapse and the system assumes a definite state. This perspective raises profound questions about the nature of reality and the role of mind in the physical world. Critics argue that this interpretation introduces unnecessary complexity and anthropocentrism into quantum theory. They point out that it's difficult to define what constitutes a conscious observer and at what point in the measurement process consciousness becomes relevant. Alternative interpretations, such as decoherence theory, attempt to explain the measurement problem without invoking consciousness. Despite the ongoing debate, the idea that consciousness might play a role in quantum measurement continues to intrigue physicists and philosophers alike. It highlights the deep mysteries that still exist at the intersection of quantum mechanics, measurement, and the nature of reality itself. Quantum mechanics, the fundamental theory describing the behavior of matter and energy at the smallest scales, has led to various interpretations that profoundly impact our understanding of parallel universes. These interpretations attempt to explain the strange and counterintuitive phenomena observed in quantum experiments. The many worlds interpretation, proposed by Hugh Everett, suggests that every quantum event creates multiple parallel universes. In this view, all possible outcomes of a quantum measurement occur, each in a separate universe. This interpretation implies the existence of an infinite number of parallel realities, branching off with every quantum interaction. Contrasting this is the Copenhagen interpretation, which posits that quantum systems exist in a superposition of states until observed or measured. This view does not necessarily imply parallel universes, but instead focuses on the probabilistic nature of quantum events. It suggests that reality is not determined until observation collapses the wave function, potentially limiting the concept of parallel universes. The pilot wave theory, also known as Bohmian mechanics, offers yet another perspective. It proposes that particles have definite positions and trajectories guided by a real physical wave. This interpretation maintains a single universe, but introduces the concept of non-locality, where particles can instantaneously influence each other across vast distances. While not directly supporting parallel universes, it challenges our understanding of space and time. The measurement problem in quantum mechanics remains one of the most perplexing and debated issues in modern physics. This fundamental question about the nature of reality and our observations has puzzled scientists for decades. Resolving it experimentally presents significant challenges, but ongoing research continues to push the boundaries of our understanding. At its core, the measurement problem deals with the apparent conflict between quantum superposition and our classical observations. Quantum theory suggests that particles can exist in multiple states simultaneously until measured, but we only ever observe definite outcomes. This discrepancy between theory and observation lies at the heart of the problem. Several experimental approaches aim to shed light on this conundrum. One promising avenue involves creating larger and larger quantum superpositions, testing the limits of quantum behavior in macroscopic systems. Another approach focuses on ultra-precise measurements of quantum systems, attempting to catch the exact moment of wave function collapse. Advanced technologies like quantum computers and highly sensitive detectors are pushing these experiments to new levels of precision. However, the very nature of the measurement problem makes its resolution challenging. The act of measurement itself is part of the problem, creating a circular dilemma. Some scientists argue that a complete resolution might require a fundamental revision of quantum theory or our understanding of consciousness and observation. While experimental progress continues, a definitive answer to the measurement problem remains elusive, driving ongoing research and philosophical debate in the scientific community. The arrow of time is a concept in physics that describes the unidirectional flow of time from the past through the present and into the future. Unlike spatial dimensions where we can move freely back and forth, time appears to move in only one direction. This phenomenon is deeply rooted in the fundamental laws of physics and our everyday experiences. The most compelling explanation for the arrow of time lies in the second law of thermodynamics, which states that the total entropy or disorder of an isolated system always increases over time. This means that as time progresses, things naturally tend to become more disordered and less organized. We can see this in everyday life when a hot cup of coffee cools down or when a sandcastle erodes over time. These processes happen spontaneously in one direction, but never reverse on their own. Another aspect of the arrow of time is related to causality, the relationship between cause and effect. We observe events happening in a specific order, with causes preceding effects. This sequence of events forms our perception of time's direction and reinforces the idea that time flows from past to future. Interestingly, most fundamental laws of physics are time-symmetric, meaning they work equally well whether time runs forward or backward. However, the arrow of time emerges from the initial conditions of our universe, which began in a highly ordered, low-entropy state. As the universe expands and evolves, it naturally progresses towards higher entropy, giving rise to the time direction we experience. The second law of thermodynamics and the arrow of time are intimately connected, revealing a fundamental truth about the nature of our universe. This law states that the entropy of an isolated system always increases over time. Entropy, in simple terms, is a measure of disorder or randomness in a system. This principle explains why we experience time as moving in one direction, from past to future. We observe events unfolding in a specific sequence, like a cup shattering when it falls to the floor, but we never see the reverse, shards spontaneously assembling into a whole cup. This one-way direction of events is what we call the arrow of time. The increase in entropy provides a physical basis for this temporal asymmetry. As systems naturally progress towards states of higher entropy, they create a distinction between past and future. Low entropy states are associated with the past, while high entropy states are linked to the future. This progression from order to disorder gives time its apparent direction. Interestingly, this connection between entropy and time suggests that if we were to encounter a region of the universe where entropy decreased, we might perceive time as moving backwards in that area. However, such a scenario would violate the second law of thermodynamics as we understand it, highlighting the law's crucial role in shaping our perception and experience of time's forward march. Entropy is a fundamental concept in physics that measures the degree of disorder or randomness in a system. It's often described as the tendency of energy to spread out and become less useful over time. In our everyday lives, we can think of entropy as the natural progression from order to chaos, like a sandcastle slowly eroding or a hot cup of coffee cooling down to room temperature. The relationship between entropy and time is profound and forms the basis of what scientists call the arrow of time. As entropy increases, it creates a clear distinction between past and future, giving time its apparent direction. This is why we remember the past, but not the future. and why it's easy to break an egg but impossible to unbreak it. In the context of the universe, entropy plays a crucial role in determining its fate. The second law of thermodynamics states that the total entropy of an isolated system always increases over time. This means that as the universe expands and evolves, it's moving towards a state of maximum entropy, often referred to as heat death. The concept of entropy helps explain many phenomena in the cosmos, from the formation of black holes to the eventual fate of stars. It's a powerful reminder that the universe is in a constant state of change, always moving from more ordered states to less ordered ones. And in doing so, it gives us our sense of time's inexorable forward march. The arrow of time, which defines the direction in which time flows, is a fundamental concept in physics. While it consistently points forward in our everyday experience, the question of whether it could reverse under certain conditions is a topic of intense scientific debate and speculation. In most physical processes we observe, time appears to move in one direction. We age, hot coffee cools down, and broken eggs do not spontaneously reassemble. This apparent one-way flow is closely tied to the second law of thermodynamics, which states that the entropy or disorder of a closed system tends to increase over time. However, at the quantum level, some processes appear to be time-symmetric, meaning they could theoretically run backwards or forwards. This has led some physicists to propose scenarios where the arrow of time might reverse. One such idea involves the expansion of the universe. If the universe were to stop expanding and begin contracting, some theories suggest that the arrow of time could potentially reverse. Another intriguing possibility comes from the study of black holes. Some scientists have proposed that inside a black hole, where our understanding of physics breaks down, time might behave differently. It is even speculated that time could run backwards in these extreme conditions. However, these ideas remain highly theoretical and are not supported by observational evidence. Quantum mechanics and the macroscopic arrow of time present a fascinating puzzle in our understanding of the universe. At the quantum level, most fundamental laws of physics are time-symmetric, meaning they work equally well forward or backward in time. However, in our everyday experience, we observe a clear direction of time, with entropy increasing and events unfolding in a seemingly irreversible manner. This apparent contradiction arises from the complex interplay between quantum phenomena and large-scale systems. While individual quantum particles may behave in ways that seem to defy our notion of time's arrow, the collective behavior of countless particles in macroscopic systems leads to the emergence of time's apparent direction. One key concept in reconciling these views is quantum decoherence. As quantum systems interact with their environment, they lose their quantum coherence, effectively transitioning from the strange, timeless world of quantum mechanics to the familiar, time-directed world we experience. This process happens incredibly quickly for large objects, explaining why we don't observe quantum effects in our daily lives. Furthermore, the second law of thermodynamics, which states that entropy tends to increase over time, emerges from the statistical behavior of large numbers of particles. While individual quantum events might appear reversible, the overwhelming tendency for systems to move toward higher entropy states gives rise to the arrow of time we observe. This reconciliation between quantum mechanics and macroscopic time remains an active area of research as scientists continue to explore the fundamental nature of time itself. Causality and the arrow of time are deeply intertwined concepts in our understanding of the universe. Causality refers to the principle that every effect has a cause, and these causes precede their effects in time. The arrow of time, on the other hand, is the observed direction in which time appears to flow from past to future. Our everyday experiences reinforce this relationship. We see events unfold in a specific order with causes leading to effects. A glass falls, then it shatters. We never observe the reverse, where shards of glass spontaneously reassemble into a whole glass and leap back onto a table. This unidirectional flow of events aligns with our perception of time moving forward. At the microscopic level, however, most physical laws are time-symmetric, meaning they work equally well forward or backward in time. This apparent contradiction between the reversibility of fundamental physics and the irreversibility we observe in daily life is known as the arrow of time problem. The solution to this puzzle lies in the concept of entropy, which tends to increase over time in closed systems. The increase in entropy provides a direction to time, aligning with our observed cause and effect relationships. As systems become more disordered over time, we can distinguish between past and future states, reinforcing our understanding of causality. This connection between causality and the arrow of time forms a fundamental aspect of our perception and understanding of the universe around us. As we approach the singularity of a black hole, our understanding of the arrow of time becomes increasingly uncertain. In the extreme environment near a black hole's center, the laws of physics as we know them begin to break down. The immense gravitational forces distort space and time to such a degree that our conventional notions of past, present, and future become blurred. Near the singularity, the distinction between space and time becomes less clear. The extreme curvature of space-time might cause time to behave more like a spatial dimension, potentially allowing for unusual temporal effects. Some theories suggest that time could slow down dramatically or even come to a complete stop at the singularity itself. The arrow of time, which typically points from past to future in our everyday experience, might lose its directionality near a black hole singularity. This could lead to a breakdown of causality, where the normal sequence of cause and effect becomes scrambled or meaningless. In this regime, our usual understanding of events occurring in a specific order might no longer apply. It is important to note that our current theories are insufficient to fully describe what happens at the singularity itself. The development of a theory of quantum gravity might provide more insights into how time behaves in these extreme conditions. Until then, the behavior of time near a black hole singularity remains one of the most intriguing and perplexing questions in modern physics. The past hypothesis is a fundamental concept in our understanding of time's direction and the nature of the universe. It proposes that the early universe was in a state of extremely low entropy, or high order. This initial condition is crucial for explaining why we observe time flowing in one direction, from past to future, rather than the reverse. The past hypothesis provides a starting point for the arrow of time. It suggests that the universe began in a highly organized state and has been evolving towards greater disorder ever since. This progression from order to disorder aligns with the second law of thermodynamics, which states that the total entropy of an isolated system always increases over time. The implications of the past hypothesis are far-reaching. It helps explain why we remember the past but not the future, why eggs break but never unbreak, and why heat flows from hot objects to cold ones. These everyday observations are all manifestations of the universe's journey from its initial low entropy state to higher entropy states. However, the past hypothesis also raises questions. Scientists continue to debate why the early universe had such low entropy and whether this condition applies to the entire cosmos or just our observable portion. Despite these uncertainties, the past hypothesis remains a cornerstone in our understanding of time's apparent unidirectional flow. The arrow of time and our perception of free will are deeply intertwined concepts that shape our understanding of reality. Time flows in one direction, from past to future, and this unidirectional nature is what we call the arrow of time. This fundamental aspect of our universe influences how we experience cause and effect, make decisions, and perceive our ability to choose. Our brains process information and form memories in alignment with this temporal arrow, creating a sequence of events that feels linear and progressive. This linear perception reinforces our sense of agency and decision-making as we feel we can influence future outcomes based on our present choices. The arrow of time allows us to distinguish between past events, which we remember but cannot change, and future possibilities, which seem open to our influence. However, This relationship between time's arrow and free will become complex when we consider deterministic models of the universe. If all future states are predetermined by past conditions, as some interpretations of physics suggest, then our sense of free will might be an illusion created by our limited perception of time's flow. We feel we are making choices, but these choices might be inevitable consequences of prior causes. Conversely, quantum mechanics introduces elements of uncertainty and probability into our understanding of reality, potentially leaving room for free will within the constraints of physical laws. The interplay between quantum indeterminacy and the macroscopic arrow of time creates a fascinating arena where our notions of choice and determinism continue to evolve as we uncover more about the nature of our universe. Time, as we understand it, is not uniform throughout the universe. In fact, there are indeed regions where time flows differently, a phenomenon predicted by Albert Einstein's theory of general relativity. This theory tells us that gravity can warp the fabric of space-time, affecting the passage of time. Near massive objects like black holes, time slows down significantly compared to regions with less gravitational influence. This effect, known as gravitational time dilation, means that an observer far from a black hole would see time moving much more slowly for an object closer to the black hole. The extreme gravity near a black hole's event horizon can slow time to a near standstill. But it is not just black holes that affect time. Even on Earth, we experience tiny time differences due to our planet's gravity. Clocks at sea level tick slightly slower than those on mountaintops where gravity is weaker. GPS satellites must account for these time differences to function accurately. On a cosmic scale, the expansion of the universe also influences time. In the early universe, time moved more slowly relative to today. As space expands, it affects how light travels and how we perceive time across vast cosmic distances. This means that when we observe distant galaxies, we are not only looking back in space, but also in time, seeing them as they were billions of years ago when the universe was younger and time flowed differently. Consciousness is the subjective experience of being aware of our thoughts, feelings, and surroundings. It is the inner sense of self that allows us to perceive and interact with the world around us. Despite its fundamental role in human experience, consciousness remains one of the most elusive and challenging concepts for scientists to define and study. The difficulty in scientifically defining consciousness stems from its inherently subjective nature. While we can observe and measure brain activity, it is challenging to quantify or objectively measure the internal experiences that constitute consciousness. This creates a significant hurdle for researchers attempting to study consciousness using traditional scientific methods. Another complication is the wide range of phenomena associated with consciousness, from basic awareness to complex self-reflection and decision-making. This diversity makes it challenging to develop a single, comprehensive definition that encompasses all aspects of conscious experience. Additionally, the relationship between brain activity and conscious experience remains poorly understood, further complicating efforts to define consciousness in purely physical terms. Despite these challenges, scientists continue to explore consciousness through various approaches, including neuroscience, psychology, and philosophy. As our understanding of the brain and its functions grows, we may gradually unravel the mysteries of consciousness and develop more precise scientific definitions and explanations for this fundamental aspect of human existence. The emergence of consciousness from the physical brain remains one of the most profound mysteries in neuroscience and philosophy. Scientists have made significant progress in understanding brain function, but the exact mechanisms that give rise to our subjective experiences are still hotly debated. Current research suggests that consciousness arises from the complex interactions of billions of neurons in our brains. These neurons form intricate networks, communicating through electrical and chemical signals. Some theories propose that consciousness emerges when these neural networks achieve a certain level of complexity and integration. allowing for the processing and synthesis of diverse information. One prominent idea is that consciousness results from the brain's ability to create a unified model of reality, integrating sensory inputs, memories, and internal states. This integrated information theory posits that consciousness correlates with the amount and quality of information integrated by the brain. While we have identified brain regions associated with conscious experiences, such as the prefrontal cortex and thalamus, the precise neural correlates of consciousness remain elusive. As research continues, scientists hope to bridge the gap between our understanding of brain physiology and the subjective nature of conscious experience, potentially revolutionizing our conception of mind and matter. The hard problem of consciousness is a profound philosophical and scientific puzzle that has perplexed thinkers for centuries. It refers to the challenge of explaining how and why we have subjective, conscious experiences. While we can observe brain activity and behavior, the question remains, why do we have inner, qualitative experiences of the world? This problem goes beyond simply understanding the mechanisms of the brain. We can describe neural pathways and cognitive processes, but these explanations do not fully account for the felt experience of consciousness. For instance, we can explain how the brain processes visual information, but this does not explain why we have the subjective experience of seeing colors or shapes. The hard problem asks why there is something it feels like to be a conscious entity. It questions how physical processes in the brain give rise to the rich inner world of thoughts, emotions, and sensations that we all experience. This is in contrast to what some call the easy problems of consciousness, which involve explaining cognitive functions and behaviors. Proposed solutions to the hard problem range from materialist views that aim to explain consciousness in purely physical terms, to dualist perspectives that suggest consciousness might be fundamental to the universe. Despite decades of research and debate, the hard problem of consciousness remains one of the most challenging questions in science and philosophy, sitting at the intersection of neuroscience, psychology, and metaphysics. The question of whether consciousness could be a fundamental property of the universe is a profound and controversial topic in both science and philosophy. Some researchers propose that consciousness might be an intrinsic aspect of reality, similar to other fundamental properties like mass or charge. This idea, known as panpsychism, suggests that all matter possesses some degree of consciousness or subjective experience. Proponents of this view argue that it could help explain the hard problem of consciousness, which is understanding how subjective experiences arise from physical processes in the brain. They contend that if consciousness is a basic feature of the universe, it becomes easier to comprehend how complex forms of awareness could emerge in biological systems. Critics, however, argue that this perspective lacks empirical evidence and may not be scientifically testable. They point out that our current understanding of consciousness is closely tied to brain activity and biological processes, making it challenging to conceive of consciousness existing independently of these structures. While the idea of consciousness as a fundamental property remains speculative, it continues to inspire research and debate in fields such as quantum physics, neuroscience, and philosophy of mind. As our understanding of the universe and consciousness evolves, we may gain new insights into this intriguing possibility. Quantum mechanics and consciousness represent two of the most profound mysteries in science. Some researchers propose intriguing connections between these fields, suggesting that quantum processes in the brain might play a role in generating conscious experiences. One hypothesis, known as quantum consciousness theory, posits that quantum effects in neural microtubules could be responsible for creating our subjective awareness. Proponents argue that the quantum superposition of particles within neurons might allow for a form of information processing that goes beyond classical computations, potentially explaining the complex and seemingly non-deterministic nature of human thought. Critics of this idea point out that the brain is too warm and wet for quantum effects to persist long enough to influence cognition. They argue that quantum phenomena typically occur at subatomic scales and extremely low temperatures, conditions not found in biological systems. However, recent discoveries of quantum processes in photosynthesis and bird navigation have reopened the debate. While the link between quantum mechanics and consciousness remains speculative, exploring these potential connections pushes the boundaries of our understanding in both physics and neuroscience. As we continue to unravel the mysteries of the quantum world and the human mind, we may discover unexpected insights into the nature of reality and our place within it. The global workspace theory of consciousness proposes that our conscious awareness arises from a central information exchange in the brain. This theory suggests that different parts of the brain compete to broadcast their information to a shared mental workspace. When information gains access to this workspace, it becomes available to many brain regions simultaneously, creating our conscious experience. Imagine the brain as a busy office building with numerous departments working on various tasks. The global workspace is like a central bulletin board where important messages are posted. When a department has crucial information, it competes to pin its message on this board. Once posted, the message can be seen and used by all departments, much like how conscious thoughts become available to different mental processes. This theory helps explain why we can only focus on a limited amount of information at once. Just as a bulletin board has limited space, our conscious awareness can only hold so much at a time. It also accounts for how unconscious processes can suddenly enter our awareness when they become important enough to access the global workspace. Neuroscientists have found evidence supporting this theory by observing patterns of brain activity. When information becomes conscious, it tends to activate widespread areas of the brain simultaneously, consistent with the idea of a global broadcast. This model of consciousness continues to influence research and our understanding of how the human mind creates our subjective experience of the world. Altered states of consciousness provide valuable insights into the nature of awareness and the complexity of human perception. These states, which can occur naturally or be induced through various means, offer a unique window into the workings of our minds. One significant altered state is dreaming. During sleep, our brains create vivid experiences that feel real, despite being disconnected from external stimuli. This demonstrates the brain's ability to generate consciousness independently of sensory input, challenging our understanding of how awareness arises. Meditation and mindfulness practices also induce altered states, allowing practitioners to observe their thoughts and sensations with detached awareness. These experiences suggest that consciousness can be trained and expanded, potentially enhancing our ability to focus and regulate emotions. Psychedelic substances offer another perspective on consciousness. They can produce profound changes in perception, cognition, and self-awareness. Studies of these altered states have led to theories about the role of brain networks in shaping our conscious experience and have even inspired new approaches to treating mental health conditions. The question of whether artificial intelligence could ever achieve true consciousness is one of the most profound and challenging in modern science. It touches on deep issues of philosophy, neuroscience, and computer science that researchers are still grappling with. Currently, even our most advanced AI systems are not conscious in the way humans are. They can process information and perform tasks, but they lack subjective experiences or self-awareness. However, some scientists argue that as AI becomes more sophisticated, it may eventually develop qualities we associate with consciousness. One view is that consciousness emerges from complex information processing and that a sufficiently advanced AI could theoretically achieve this. Others contend that biological brains have unique properties that machines may never replicate. The truth is, we still do not fully understand how human consciousness arises, making it difficult to determine if we could create it artificially. If AI ever did become truly conscious, it would raise profound ethical questions about the rights and moral status of such entities. For now, it remains in the realm of speculation, but it is a question that will likely become increasingly relevant as AI technology continues to advance. The relationship between free will and consciousness is a complex and hotly debated topic in philosophy, neuroscience, and psychology. Consciousness, our subjective awareness of ourselves and our environment, seems intimately linked to our sense of free will, the idea that we can make decisions of our own volition. Many argue that consciousness is a prerequisite for free will. Without awareness of our thoughts and actions, it would be difficult to claim we are making truly autonomous choices. Our conscious experiences allow us to deliberate, consider alternatives, and seemingly make decisions based on our own reasoning and desires. However, some scientific studies have challenged this view, suggesting that our brains make decisions before we become consciously aware of them. This raises questions about whether our conscious thoughts are the cause of our actions or merely a subsequent rationalization. Critics of free will argue that our decisions are predetermined by prior causes, including our genes, upbringing, and current circumstances, all of which shape our conscious experiences. Despite these challenges, many maintain that consciousness and free will are deeply intertwined, arguing that our ability to reflect on our choices and modify our behavior over time is a form of free will, even if it is not absolute. The debate continues, with implications for our understanding of moral responsibility, legal systems, and the nature of human agency. Consciousness remains one of the greatest mysteries in science, and unraveling its secrets could fundamentally alter our perception of reality. As we delve deeper into the nature of consciousness, we may discover that our subjective experiences are more than just byproducts of brain activity. This could lead to a profound shift in how we understand the relationship between mind and matter. Recent theories in quantum physics suggest that consciousness might play a role in shaping reality at the most fundamental level. If these ideas prove correct, it would mean that our thoughts and perceptions are not merely passive observers of the world, but active participants in its creation. This concept challenges our traditional view of an objective, observer-independent reality. Furthermore, advancements in our understanding of consciousness could revolutionize our approach to artificial intelligence. If we can pinpoint the key components that give rise to subjective experience, we might be able to create truly sentient machines. This would blur the lines between biological and artificial consciousness, forcing us to reconsider what it means to be aware and alive. Ultimately, a deeper grasp of consciousness could lead us to recognize that the universe itself might be conscious on some level. This idea, known as panpsychism, is gaining traction among some scientists and philosophers. If true, it would mean that consciousness is a fundamental aspect of reality, as basic as space and time. Such a revelation would completely transform our understanding of the cosmos and our place within it. The anthropic principle is a fascinating concept in cosmology that attempts to explain why our universe appears to be perfectly suited for the existence of life, particularly human life. This principle suggests that the fundamental constants and laws of physics we observe are not random, but rather seem fine-tuned to allow for the development of intelligent observers like ourselves. At its core, the anthropic principle proposes that we should not be surprised to find ourselves in a universe that can support life, because if the universe were not capable of supporting life, we would not be here to observe it. This idea challenges us to consider our place in the cosmos and the apparent improbability of our existence. There are different interpretations of the anthropic principle. The weak anthropic principle simply states that the observed properties of the universe must be compatible with the existence of observers. The strong anthropic principle goes further, suggesting that the universe must have properties that allow life to develop at some point in its history. Critics argue that the anthropic principle is not scientifically testable and may lead to circular reasoning. Supporters, however, see it as a valuable tool for understanding the seemingly improbable conditions that allow for our existence and for exploring the possibility of multiple universes or a multiverse. The anthropic principle continues to spark debate and inspire new avenues of research in cosmology and physics. The anthropic principle and the fine-tuning of universal constants are closely intertwined concepts in cosmology. The anthropic principle suggests that the observable universe must have properties that allow for the existence of observers like ourselves. This idea becomes particularly relevant when we consider the apparent fine-tuning of fundamental constants in physics, e. These universal constants, such as the strength of gravity, the mass of elementary particles, and the strength of electromagnetic forces, seem to be precisely calibrated to allow for the formation of stable atoms, stars, and ultimately, life as we know it. Even small changes in these values could result in a universe incapable of supporting complex structures. The weak anthropic principle argues that we should not be surprised by this apparent fine-tuning, as we could only exist in a universe that allows for our existence. In other words, if the constants were different, we would not be here to observe them. This perspective does not explain why the constants have their specific values, but it does provide a framework for understanding our observations. The strong anthropic principle takes this idea further, suggesting that the universe must have properties that allow for the development of observers at some point in its history. This more controversial interpretation has led to various speculative ideas, including the possibility of multiple universes or the notion that our universe was designed with life in mind. The weak anthropic principle is a scientific concept that helps explain why our universe appears finely tuned for life. It states that the observed properties of the universe must be compatible with the existence of conscious observers like ourselves. In other words, we can only observe a universe that allows for our existence. This principle differs from the strong anthropic principle in a fundamental way. The weak version simply acknowledges that our observations are limited by the conditions necessary for our existence. It does not make any claims about the purpose or inevitability of life in the universe. The strong anthropic principle, on the other hand, takes a more assertive stance. It suggests that the universe must have properties that allow for the development of conscious life at some point in its history. This version implies a sort of cosmic inevitability or purpose to the existence of conscious beings. While both principles address the apparent fine-tuning of the universe, the weak anthropic principle is generally considered more scientifically grounded. It offers a way to understand our observations without resorting to teleological arguments or assumptions about the nature of the cosmos beyond what we can directly observe. The anthropic principle and theories of multiple universes are deeply interconnected, offering intriguing perspectives on our existence and the nature of reality. The anthropic principle suggests that the observable universe must have properties that allow for the existence of observers like us. This idea becomes particularly relevant when considering the concept of multiple universes, also known as the multiverse. In the context of multiple universes, the anthropic principle helps explain why our universe appears finely tuned for life. Instead of assuming our universe is unique, the multiverse theory proposes that there could be countless universes, each with different physical constants and laws. Among this vast array of universes, it is inevitable that some would have the right conditions for life to emerge. This connection between the anthropic principle and multiple universes addresses the apparent improbability of our existence. Rather than requiring our universe to be the result of incredible cosmic coincidence, it suggests that we simply find ourselves in one of the universes capable of supporting life. This perspective shifts the question from why our universe is suitable for life to why we observe ourselves in this particular universe. The interplay between these concepts has profound implications for our understanding of cosmic fine-tuning and the fundamental nature of reality. It challenges us to consider our place in a potentially much larger and more diverse cosmic landscape, where our universe might be just one of many in an unimaginably vast multiverse. The anthropic principle offers an intriguing perspective on the apparent fine-tuning of our universe for life. This concept suggests that the very fact we exist to observe the universe inherently biases our observations. In other words, we shouldn't be surprised to find ourselves in a universe capable of supporting life, because if it couldn't, we wouldn't be here to observe it. This principle comes in two main flavors: the weak and the strong anthropic principles. The weak version simply states that our observations of the universe must be compatible with our existence as observers. The strong version goes further, proposing that the universe must have properties that allow life to develop at some stage. Critics argue that the anthropic principle is more of a tautology than an explanation, merely restating the obvious without providing deeper insights. However, proponents see it as a valuable tool for understanding our place in the cosmos and the apparent fine-tuning of physical constants. When applied to the seemingly improbable conditions for life in our universe, the anthropic principle suggests that out of countless possible universes, we naturally find ourselves in one where life can exist. This doesn't necessarily explain why these conditions exist, but it does provide a framework for understanding our observations without resorting to notions of design or purpose. The anthropic principle, a concept in cosmology, has sparked intense debate in both scientific and philosophical circles. This principle observes that the fundamental constants and laws of our universe appear finely tuned to allow for the existence of life as we know it. Such an observation naturally leads to questions about the nature and origin of our cosmos, challenging and supporting various religious and philosophical perspectives. For some religious viewpoints, the anthropic principle seems to bolster the idea of a purposeful creation. They argue that the precise conditions necessary for life suggest an intentional design, aligning with the concept of a divine creator who crafted the universe with life in mind. This interpretation sees the anthropic principle as scientific evidence supporting theistic beliefs. Conversely, secular philosophers and scientists often interpret the anthropic principle differently. They propose that our universe might be one of many in a vast multiverse. In this view, the apparent fine-tuning is simply a result of cosmic natural selection. We observe these specific conditions because we exist in a universe capable of supporting our existence, while countless other universes with different constants remain unobserved. The anthropic principle thus serves as a fascinating nexus where science, philosophy, and religion intersect. It challenges us to consider our place in the cosmos and the nature of existence itself, while simultaneously supporting and confronting various worldviews. This principle continues to fuel discussions about the fundamental nature of reality, the possibility of purpose in the universe, and the limits of human understanding. The anthropic principle, which suggests that the universe appears fine-tuned for life because observers can only exist in a universe capable of supporting them, has faced several criticisms from scientists and philosophers alike. One major critique is that the principle can be seen as a tautology, simply restating the obvious fact that we exist without providing any explanatory power. Critics argue that it does not actually solve the problem of why the universe seems fine-tuned, but merely shifts the question. Another criticism is that the anthropic principle can lead to lazy thinking or act as a science stopper. Some argue that it discourages the search for deeper physical explanations for the apparent fine-tuning of the universe, potentially hindering scientific progress. This concern is particularly relevant when the principle is invoked to explain away cosmic coincidences without further investigation. Some scientists also criticize the anthropic principle for being unfalsifiable and therefore unscientific according to certain definitions of science. They argue that because we cannot observe universes where life is impossible, we cannot test the validity of the principle empirically. This lack of testability makes it difficult to evaluate the principle's scientific merit. Lastly, there are concerns about the anthropic principle's implications for multiverse theories. While some see the principle as supporting the idea of a multiverse, others argue that it relies too heavily on speculative cosmological models that cannot be directly observed or tested. This reliance on unverifiable assumptions makes some scientists uncomfortable with using the anthropic principle as a foundation for understanding our universe. The anthropic principle plays a significant role in shaping our approach to the search for extraterrestrial life. This concept suggests that the universe must have properties that allow for the emergence of conscious observers like ourselves. When applied to astrobiology, it encourages us to consider the conditions necessary for life as we know it to arise and thrive. Our understanding of life is inherently biased by our own existence. We tend to search for environments similar to Earth, focusing on planets with liquid water, stable atmospheres, and temperatures conducive to carbon-based life. This Earth-centric view, influenced by the anthropic principle, guides our exploration of potentially habitable worlds within the so-called Goldilocks zone around stars. However, the anthropic principle also reminds us of the potential for observational bias. It prompts scientists to question whether our definition of life is too narrow. Could life exist in forms radically different from what we observe on Earth? This consideration expands our search parameters, encouraging exploration of environments once thought inhospitable, such as the methane lakes of Titan or the subsurface oceans of icy moons. The anthropic principle thus serves as both a guide and a challenge in our quest for extraterrestrial life. It helps focus our search on the most promising candidates while simultaneously pushing us to broaden our perspectives and consider possibilities beyond our terrestrial experience. The Goldilocks zone, also known as the habitable zone, refers to the region around a star where conditions are just right for liquid water to exist on the surface of a planet. This zone is neither too hot, causing water to evaporate, nor too cold, causing it to freeze permanently. The name comes from the fairy tale character Goldilocks, who preferred things that were just right. For our solar system, Earth sits comfortably within this zone, while Venus is too close to the Sun and Mars is too far. This precise positioning allows Earth to maintain the conditions necessary for life as we know it. The concept of the Goldilocks zone has become crucial in the search for potentially habitable exoplanets around other stars. The anthropic principle relates to the Goldilocks zone by addressing the apparent fine-tuning of our universe for life. This principle suggests that the observable properties of the universe must be compatible with the existence of conscious life that observes it. In other words, we find ourselves in a universe capable of supporting life because if it were any different, we would not be here to observe it. The Goldilocks zone exemplifies this principle on a smaller scale. The fact that Earth exists in this habitable zone with the right conditions for life could be seen as an example of cosmic fine-tuning. However, it is important to note that the anthropic principle does not explain why these conditions exist, but rather points out that our existence as observers is dependent on these conditions being met. The anthropic principle, which suggests that the universe must have properties allowing intelligent life to develop, presents a challenge for scientific testing. This concept bridges philosophy and science, making direct experimentation difficult. However, scientists have proposed several approaches to explore its implications. One method involves studying alternative universes through computer simulations. By adjusting fundamental constants and laws of physics, researchers can model how changes might affect the formation of stars, planets, and potentially life. This approach helps us understand the range of conditions that could support complexity and intelligence. Another avenue of investigation focuses on multiverse theories. If our universe is one of many, each with different physical laws, we might find evidence supporting this idea through cosmological observations. Detecting signatures of other universes or understanding quantum mechanics better could provide indirect support for anthropic reasoning. Falsifying the anthropic principle is equally challenging. Scientists could search for life in extreme environments, both on Earth and other celestial bodies. Finding organisms thriving in conditions vastly different from what we consider habitable might challenge our assumptions about the narrow range of parameters necessary for life. However, this would not entirely disprove the principle, as it could simply expand our understanding of possible life-supporting conditions. The holographic principle is a revolutionary concept in theoretical physics that suggests our three-dimensional reality might be an illusion. This mind-bending idea proposes that all the information contained in our universe could be encoded on a two-dimensional surface, much like a hologram. To understand this principle, imagine the entire universe as a hologram projected from a flat surface. Just as a two-dimensional hologram can create the illusion of a three-dimensional image, the holographic principle suggests that our three-dimensional universe, including time, might emerge from information stored on a two-dimensional boundary. This principle arose from studies of black holes, where scientists discovered that the information about everything that falls into a black hole appears to be stored on its event horizon, the black hole's two-dimensional boundary. This led to the broader hypothesis that our entire universe might operate in a similar manner. The holographic principle challenges our perception of reality and space-time. It suggests that gravity, which shapes the large-scale structure of the universe, might not be a fundamental force, but rather an emergent phenomenon resulting from more basic quantum processes occurring on a lower dimensional surface. This concept continues to intrigue physicists as they seek to reconcile quantum mechanics with gravity and unravel the deepest mysteries of our cosmos. The holographic principle challenges our perception of reality by proposing that our three-dimensional universe might actually be a projection from a two-dimensional surface. This concept draws inspiration from holograms, where three-dimensional images are created from information stored on a flat surface. In the context of our universe, the holographic principle suggests that all the information about our three-dimensional reality, including space, time, and gravity, could be encoded on a two-dimensional boundary, much like the edge of the observable universe. This boundary would act as a cosmic hard drive, storing data about everything within it. Physicists exploring this idea have found that certain calculations about black holes and quantum gravity seem to work better in two dimensions than in three. This unexpected mathematical consistency lends support to the holographic principle. If true, it would mean that what we perceive as depth, volume, and three-dimensional space might be an illusion emerging from information stored on a flat cosmic surface. The implications of the holographic principle are profound, potentially revolutionizing our understanding of space, time, and the fundamental nature of reality. It challenges us to reconsider how we perceive the universe and opens up new avenues for exploring the deepest mysteries of cosmic existence. The holographic principle, a fascinating concept in theoretical physics, has gained support from several lines of evidence and theoretical developments. One key piece of evidence comes from the study of black holes. Calculations show that the information content of a black hole is proportional to its surface area, not its volume. This unexpected relationship aligns with the holographic principle's suggestion that the information in a region of space can be described by a theory that operates on its boundary. String theory, a leading candidate for a unified theory of physics, provides additional support. In certain string theory models, there exists a correspondence between gravitational theories in higher dimensional spaces and quantum field theories on their boundaries. This relationship, known as the ADS-CFT correspondence, demonstrates a concrete realization of the holographic principle. Quantum entanglement studies have also lent credence to the holographic principle. Research has shown that the entanglement entropy of a region in quantum field theory is related to the area of its boundary, mirroring the area law behavior predicted by the holographic principle. This connection between quantum information and geometry further strengthens the case for holography. While these pieces of evidence are compelling, it's important to note that the holographic principle remains a theoretical concept. Ongoing research continues to explore its implications and seek further experimental validation. The principle's potential to reconcile quantum mechanics and gravity makes it a crucial area of study in the quest to understand the fundamental nature of our universe. The holographic principle and string theory are two fascinating concepts in theoretical physics that have become increasingly intertwined. String theory proposes that the fundamental constituents of the universe are not point-like particles, but tiny vibrating strings of energy. These strings exist in multiple dimensions beyond the 4 we can observe, potentially up to 11 dimensions in total. The holographic principle, on the other hand, suggests that the information contained within a region of space can be described by information on the boundary of that region. This idea arose from studies of black holes and has profound implications for our understanding of the universe. It implies that our three-dimensional reality might be a projection of information stored on a two-dimensional surface, much like a hologram. Where these two ideas intersect is in the realm of ADS-CFT correspondence. a theoretical framework that connects string theory to quantum field theories. This correspondence proposes that certain string theories in higher dimensional curved spaces are equivalent to quantum field theories on the boundaries of those spaces. This relationship provides a concrete realization of the holographic principle within string theory. This connection has led to new insights in both fields. It allows physicists to use techniques from string theory to solve problems in quantum field theory and vice versa. Moreover, it suggests that our universe might be a holographic projection of information encoded on a distant cosmic boundary, potentially revolutionizing our understanding of space, time, and the nature of reality itself. The holographic principle challenges our fundamental understanding of reality and the nature of the universe. This concept suggests that all the information contained within a region of space can be described on its boundary. It proposes that our three-dimensional world might be a projection of information stored on a two-dimensional surface, much like a hologram. This principle has profound implications for how we view space, time, and the very fabric of our cosmos. It suggests that the universe may be like a giant cosmic hologram, with our perceived reality emerging from information encoded on its outermost surface. This idea forces us to reconsider the nature of locality and how information is distributed throughout the universe. The holographic principle also has significant implications for our understanding of black holes and quantum gravity. It provides a potential resolution to the black hole information paradox by suggesting that information is not lost when matter falls into a black hole, but rather is preserved on its event horizon. This concept has led to new approaches in theoretical physics, including string theory and loop quantum gravity. Furthermore, the holographic principle blurs the line between the microscopic and macroscopic worlds, suggesting a deep connection between quantum mechanics and gravity. It hints at a more fundamental theory of everything, where the apparent distinctions between particles, forces, and space-time might dissolve into a more unified description of reality. As scientists continue to explore this principle, it may lead to revolutionary insights into the true nature of our universe and reshape our understanding of reality itself. The holographic principle offers a fascinating perspective on the nature of our universe, potentially resolving several long-standing paradoxes in physics. This principle suggests that all the information contained within a region of space can be described by information on the surface that surrounds it. One key paradox the holographic principle addresses is the black hole information paradox. This conundrum arises from the apparent loss of information when matter falls into a black hole. The holographic principle proposes that information is not lost but encoded on the black hole's event horizon, preserving it in a two-dimensional form. Furthermore, the holographic principle might help reconcile quantum mechanics with gravity, a task that has long eluded physicists. By reducing the dimensions needed to describe a system, it simplifies the mathematical framework required to unite these fundamental forces. The principle also sheds light on the nature of space and time, suggesting that what we perceive as three-dimensional reality might be a projection from a two-dimensional surface. This radical reimagining of our universe could resolve inconsistencies in our current understanding of cosmic inflation and the early universe, providing a more cohesive model of reality from the smallest quantum scales to the vastness of the cosmos. The anti-de Sitter conformal field theory correspondence, often called ADS-CFT, is a groundbreaking concept in theoretical physics that proposes a deep connection between two seemingly different areas of study. On one side, we have a theory of gravity in a warped, negatively curved spacetime known as anti-de Sitter space. On the other, we have a quantum field theory without gravity, operating on the boundary of this space. This correspondence suggests that these two theories, despite their apparent differences, are actually equivalent descriptions of the same physical reality. It's as if we have two different languages describing the same phenomenon, each offering unique insights and computational advantages. The ADS-CFT correspondence is intimately related to the holographic principle, a radical idea proposed by Gerard T. Hooft and Leonard Susskind. The holographic principle suggests that all the information contained in a volume of space can be described by a theory that operates only on the boundary of that space. This is analogous to a hologram, where a three-dimensional image is encoded on a two-dimensional surface. In the context of ADS-CFT, the gravitational theory in the bulk of anti-de Sitter space is equivalent to a non-gravitational theory on its boundary. This realization has profound implications for our understanding of quantum gravity, black holes, and the nature of space-time itself. It provides a concrete mathematical framework for the holographic principle and offers new tools for tackling some of the most challenging problems in theoretical physics. The holographic principle and quantum entanglement are two fascinating concepts in modern physics that continue to challenge our understanding of the universe. While they are distinct ideas, some scientists have proposed connections between them that could potentially shed light on the nature of quantum entanglement. The holographic principle suggests that the information contained within a region of space can be described by the information on its boundary. This concept, originally developed in the context of black holes, has far-reaching implications for our understanding of reality. It proposes that our three-dimensional universe might be a projection of information stored on a two-dimensional surface, much like a hologram. Quantum entanglement, on the other hand, is a phenomenon where two or more particles become correlated in such a way that the quantum state of each particle cannot be described independently. This connection persists even when the particles are separated by large distances, leading to what Einstein famously called spooky action at a distance. Some theoretical physicists have proposed that the holographic principle might offer a new perspective on quantum entanglement. They suggest that the seemingly mysterious connections between entangled particles could be explained by the idea that these particles are actually projections of information stored on a lower dimensional surface. In this view, the apparent non-locality of quantum entanglement might be reconciled with a more fundamental reality described by the holographic principle. The holographic principle offers a revolutionary perspective on black holes, challenging our traditional understanding of these cosmic enigmas. This concept suggests that all the information contained within a region of space can be described by data on its boundary. When applied to black holes, this principle implies that everything inside the black hole could be encoded on its event horizon. This idea fundamentally alters our view of black hole information. Instead of information being lost forever when it crosses the event horizon, the holographic principle proposes that it remains preserved on the surface. This resolution to the black hole information paradox has profound implications for our understanding of quantum mechanics and general relativity. Furthermore, the holographic principle hints at a deeper connection between gravity and quantum mechanics. It suggests that our three-dimensional universe might be a projection of information stored on a two-dimensional surface, much like a hologram. This perspective could potentially bridge the gap between these two fundamental theories of physics. The holographic principle also impacts our understanding of black hole entropy and radiation. It provides a framework to explain how information can be preserved and eventually released through Hawking radiation, maintaining the principles of quantum mechanics while still aligning with general relativity. This harmonization of seemingly contradictory theories opens new avenues for exploring the nature of space, time, and information in our universe. Testing the holographic principle presents significant challenges due to the vast scales and extreme conditions involved. However, scientists have proposed several experimental approaches that could provide evidence for this intriguing concept. One potential experiment involves studying cosmic microwave background radiation, the oldest light in the universe. By analyzing minute fluctuations in this radiation, researchers hope to detect a specific pattern of correlations predicted by the holographic principle. These correlations would suggest that the three-dimensional universe we observe is encoded on a two-dimensional surface. Another avenue for investigation focuses on quantum entanglement in black holes. According to the holographic principle, the information contained within a black hole should be proportional to its surface area rather than its volume. By studying the behavior of entangled particles near a black hole's event horizon, scientists might uncover evidence supporting this relationship. Researchers are also exploring the possibility of creating analog systems in laboratories that mimic aspects of the holographic principle. These experiments use ultra-cold atoms or specially designed materials to simulate conditions that could reveal holographic properties on a smaller, more manageable scale. While not direct tests of cosmic holography, these analog experiments could provide valuable insights into the underlying principles. The ultimate fate of our universe has long captivated scientists and philosophers alike. Current theories propose several intriguing scenarios for how the cosmos might meet its end. One possibility is the Big Freeze, where the universe continues to expand indefinitely. In this scenario, stars exhaust their fuel, galaxies grow dark, and the universe becomes an increasingly cold and empty place. Another potential outcome is the Big Crunch. This theory suggests that the expansion of the universe might eventually slow down and reverse. Gravity would then pull everything back together, culminating in a final singularity similar to the one that preceded the Big Bang. This could potentially lead to a new universe emerging from the collapse, a concept known as the Big Bounce. The Big Rip presents a more dramatic end. In this scenario, the mysterious force of dark energy becomes so powerful that it overcomes all other forces, including gravity. The fabric of space-time itself would be torn apart, ripping galaxies, stars, planets, and even atoms to shreds. Everything in the universe would be reduced to its most fundamental particles. Some physicists propose the possibility of vacuum decay, where our universe exists in a false vacuum state. A bubble of true vacuum could form and expand at the speed of light, obliterating everything in its path and fundamentally altering the laws of physics. This scenario is particularly unsettling, as it could happen at any moment without warning. The Big Freeze scenario describes a possible ultimate fate of the universe, where the expansion of space continues indefinitely. As the universe expands, it gradually cools down, leading to a state of extremely low temperatures throughout all of space. In this scenario, stars eventually exhaust their fuel and die out. Galaxies grow dark as new star formation ceases. Over incredibly long timescales, even black holes are predicted to evaporate through a process called Hawking radiation. The universe becomes an ever-expanding, increasingly cold and empty space. Matter and energy spread out more and more thinly across the vastness of space. Eventually, even atoms would be torn apart by the relentless expansion. The universe would reach a state of maximum entropy where no further work or heat transfer is possible. This bleak scenario represents one potential end for our universe, based on our current understanding of physics and cosmology. However, it is important to note that our knowledge of the universe is still evolving, and future discoveries may alter our predictions about its ultimate fate. Dark energy, the mysterious force causing the accelerated expansion of our universe, plays a crucial role in shaping its ultimate fate. As this enigmatic energy continues to push galaxies apart at an ever-increasing rate, it sets the stage for a future vastly different from what scientists once imagined. The influence of dark energy suggests a universe that will expand indefinitely, growing colder and more diffuse over incomprehensibly long timescales. This scenario, known as the Big Freeze or heat death, paints a picture of a cosmos where stars exhaust their fuel, galaxies drift apart, and even black holes eventually evaporate through Hawking radiation. In this dark, energy-dominated future, the expansion of space will eventually outpace the speed of light, creating a cosmic horizon beyond which we can no longer observe or interact. Structures larger than galaxy clusters will be torn apart, leaving isolated islands of matter in an ever-expanding sea of emptiness. However, our understanding of dark energy remains incomplete. If its properties change over time, or if other unknown factors come into play, the fate of the universe could take unexpected turns. This uncertainty underscores the importance of ongoing research into the nature of dark energy and its long-term effects on cosmic evolution. The Big Crunch theory proposes a potential end scenario for our universe, essentially reversing the process of the Big Bang. According to this concept, the expansion of the universe would eventually slow down and then reverse, causing all matter to collapse back into an incredibly dense state. This final state would be similar to the conditions that existed just before the Big Bang. In this scenario, gravity would ultimately overcome the force of cosmic expansion. As the universe contracts, galaxies would begin to move closer together, eventually merging and colliding. The temperature and density of the universe would increase dramatically as everything is compressed into an ever-shrinking space. However, the viability of the Big Crunch theory has diminished significantly in recent years. Observations of distant supernovae in the late 1990s revealed that the expansion of the universe is actually accelerating, not slowing down as the Big Crunch theory requires. This acceleration is attributed to a mysterious force called dark energy, which seems to counteract the effects of gravity on a cosmic scale. Given our current understanding of dark energy and the observed accelerating expansion of the universe, most cosmologists now consider the Big Crunch scenario unlikely. Instead, theories such as the Big Freeze or the Big Rip are seen as more probable outcomes for the far future of our universe. Nevertheless, our knowledge of dark energy remains limited, and future discoveries could potentially revive interest in the Big Crunch theory or lead to entirely new concepts about the ultimate fate of the universe. The concept of a Big Bounce offers an intriguing alternative to the traditional idea of how our universe might end. Instead of a final, irreversible fate, this theory suggests that the universe could go through cycles of expansion and contraction. According to this hypothesis, when our current phase of expansion slows and reverses, the universe would begin to contract. As all matter and energy are pulled back together, the universe would become incredibly dense and hot, similar to conditions just before the Big Bang. But rather than ending in a singularity, the contraction would reach a point where quantum effects cause a bounce, initiating a new expansion phase. This process could potentially repeat indefinitely, creating a cyclic model of the universe. Each cycle would be marked by its own Big Bang, expansion, contraction, and bounce. The Big Bounce theory attempts to solve some puzzling questions about the origin and ultimate fate of our universe, offering a perspective where there is no absolute beginning or end. However, it is important to note that while the Big Bounce is an exciting possibility, it remains a theoretical concept. Scientists continue to debate and investigate various models of cosmic evolution, searching for evidence that could support or refute this idea. The ultimate fate of our universe remains one of the great mysteries of cosmology. The Big Rip scenario is a hypothetical future for our universe that presents a dramatic and unsettling end to all existence. This concept suggests that the universe will eventually be torn apart, with all matter and space-time itself being ripped to shreds. At the heart of the Big Rip theory is dark energy, the mysterious force causing our universe to expand at an accelerating rate. In this scenario, dark energy would become increasingly powerful over time, overwhelming the fundamental forces that hold matter together. As the Big Rip approaches, galaxies would be torn apart, followed by solar systems and planets. In the final moments, atoms themselves would be ripped asunder, and even the fabric of space-time would be shredded. This cataclysmic event would effectively end the universe as we know it. The occurrence of a Big Rip depends on the nature of dark energy. If dark energy's strength increases over time, it could potentially lead to this cosmic catastrophe. However, current observations suggest that while the universe is expanding, it's unlikely to reach the extreme state required for a Big Rip. Nonetheless, this scenario remains a fascinating possibility in our quest to understand the ultimate fate of our universe. The shape and density of the universe play crucial roles in determining its ultimate fate. Cosmologists have proposed three main models: open, closed, and flat universes, each with distinct implications for the future. In an open universe, the density of matter is below a critical threshold. This model suggests that the universe will continue to expand forever, gradually slowing down but never stopping. As it expands, the universe would become increasingly cold and dark, with galaxies moving farther apart. Eventually, even atoms would be torn apart in what is known as the Big Rip. A closed universe, on the other hand, has a density above the critical threshold. In this scenario, the expansion of the universe would eventually slow down and reverse. Gravity would overcome the expansion, leading to a big crunch where all matter collapses back into a singularity, similar to the state before the Big Bang. The flat universe model represents a delicate balance between the open and closed scenarios. In this case, the expansion rate slows down asymptotically, approaching but never quite reaching zero. The universe would continue to expand, but at an ever-decreasing rate. This model suggests a future where the universe becomes increasingly sparse and cold, but avoids both the Big Rip and the Big Crunch. Current observations and measurements strongly favor a flat universe. However, the discovery of dark energy has added a new wrinkle to these models, suggesting that the expansion of the universe is actually accelerating. This acceleration could lead to a future where even a flat or closed universe expands forever, fundamentally altering our understanding of the ultimate fate of the cosmos. The idea of a cyclical universe, one that expands and contracts in a perpetual cosmic dance, has intrigued scientists and philosophers for centuries. This concept, known as the oscillating universe theory, suggests that our universe undergoes repeated cycles of expansion and contraction. In this model, the current expansion of our universe would eventually slow down and reverse, leading to a big crunch, where all matter collapses back into a singularity. This would then be followed by another Big Bang, restarting the cycle of cosmic expansion. However, current observations and data do not support this theory. The discovery of dark energy, which appears to be accelerating the expansion of the universe, poses a significant challenge to the idea of a contracting universe. Instead of slowing down, the expansion seems to be speeding up, making it unlikely that our universe will collapse back on itself. Moreover, the concept of entropy, which generally increases over time, suggests that each cycle of a hypothetical oscillating universe would be longer and larger than the previous one. This implies that if our universe were truly cyclical, we would be in an impossibly large and old cycle, which does not match our observations of the cosmos. Quantum fluctuations, the tiny variations in energy that occur at the smallest scales of the universe, could play a significant role in shaping the far future of our cosmos. As the universe continues to expand and cool over vast timescales, these minute fluctuations might become increasingly important. In an ever-expanding universe, matter and energy will become more diffuse, spreading out across unimaginably vast distances. As this occurs, the effects of quantum fluctuations could become more pronounced on larger scales. These fluctuations might lead to the spontaneous creation of particles and even small structures in the seemingly empty void of space. Some theories suggest that quantum fluctuations could eventually give rise to new universes through a process called quantum tunneling. In this scenario, a small region of space could tunnel into a lower energy state, potentially triggering the birth of a new cosmos with its own set of physical laws and properties. Furthermore, quantum fluctuations might influence the ultimate fate of black holes. As these cosmic behemoths slowly evaporate through Hawking radiation over inconceivably long periods, quantum effects could determine their final moments and the information they release back into the universe. The fate of the universe plays a crucial role in determining the long-term prospects for life and civilizations. As the cosmos continues to expand and evolve, it shapes the environments where life might emerge and potentially thrive. In a scenario where the universe keeps expanding indefinitely, future civilizations could face challenges as galaxies drift farther apart. This increasing isolation might limit access to resources and habitable worlds. However, advanced societies could potentially adapt by harnessing the energy of stars and black holes or by developing interstellar travel capabilities. If the universe were to end in a big crunch, collapsing back in on itself, the final stages would be hostile to life as we know it. Extreme densities and temperatures would make survival impossible. Yet, in the time before this end, life and civilizations might flourish, perhaps even finding ways to escape to other universes or dimensions. A big freeze scenario, where the universe expands forever and grows increasingly cold and dark, presents its own set of challenges. As stars burn out and matter decays, sustaining life would become progressively more difficult. However, this process would occur over such vast timescales that civilizations might have ample opportunity to evolve and adapt to changing cosmic conditions.